Dear delegates, we'll wait for a few more minutes so that participants can join.
Dear ICONN attendants, it is my great pleasure to take part to the 7th edition of the International Conference on Nanoscience and Nanotechnology. I do congratulate the organizers of the conference to assemble a terrific program open to all of the many aspects of low-dimensional physics and technology. Nanoscience and nanotechnology are established pillars of the current science and technology. They provide a formidable ground to develop and invent new devices, products, and systems aimed at improving the wellness of human beings. As scientists, we have to be aware of these great expectations and have to be committed to do our best to honor them. For the second year, the University of Rome Tor Vergata proudly cooperates to the organization of ICONN. I ensure the continuous support of my university for next editions, and I do hope that this presence may foster scientific and cultural collaborations among all the participants to the conference. My best wishes for a fruitful ICONN 2023.
Good day, everyone. My name is Edward Cheng. I'm glad that I could join ICON 2023 this year. I have been joining this meeting for several times in the past few years, and I'm glad to see everyone in the meeting again. I think during the past few years, we have been working on the nanotechnology, even though we will not be able to meet each other in person. But I think our progress is still quite large, and also everybody is really enthusiastic in making the technology viable to the community. And this time I am here, and I hope that we can, because the semiconductor is getting more and more important and link the world close together through the technology. So I hope through this meeting we can know better what our progress in the past 3 years, and we can make better use of what we have did for the future, and then we can have find the good topics we can work together. So I think this conference is actually very helpful in combining the people from different parts of the world together and know what we are doing. I'm glad that I'm able to deliver the talk this time, and I hope that you will enjoy the conference and that we can learn something from each other, and we can meet each other in the future in person, and then exchange all kind of ideas. I wish that everybody good health, and that we can have many fruitful interaction in the future. Thank you.
Uh, I thank personally I thank Professor Carola Di Natale from University of Rome, Tor Vergentana, Italy, and Professor Edward E. Chang from NCTU Taiwan, okay, for their wonderful greetings regarding this icon. Okay. Hello everyone. I would like to yes, I welcome you all for the second day afternoon session of this icon. In this session, we have two delegates for their keynote lectures, and the session chair is Dr. S.T. Aruna from CSIR National Aerospace Laboratories, Bangalore, and her research interests right from the nanomaterial synthesis, ceramics material processing, plasma spray coatings, for fabrication of high temperature electrochemical devices. He's also interested in design and development of plasma sprayed thermal barrier coatings and coatings for biomedical wear resistant applications. She also contributed for producing the chemical traces at low cost to study the flow phenomenon in pulse jet engines. And on the top of that, she have 660 journal articles she have contributed, and she had actually published 15 number of book chapters, and she won 32 number of patents in her credit. I welcome you, ma'am. Please, ma'am, kindly take the charge of this chairman. Please.
Yeah. Thank you, Shiva, for the introduction. But I would like to correct that I have only 160 journal articles and patents are 12. The number 3 and 6 are not correct. Okay. So thank you so much. And thank you, organizers, for giving me this opportunity to chair this session. So I welcome you all for this afternoon session. The keynote lecture 9 will be delivered by Professor Jatindra Kumar Rath, Department of Physics, Indian Institute of Technology, Madras, Chennai. So, Professor Rath has about 230 papers to his credit, 4 book chapters, and H index of 60. And his research interests are in the area of photovoltaics, nanomaterials, and solar cells. And he is currently editor of Journal of Material Science, Materials in Electronics. So I request Professor Jatinder Kumar Rath to deliver the keynote lecture on prospects of silicon-based quantum dots for third generation solar cells. Professor Jatinder Rath, please. I request you to deliver the lecture.
Thank you, Dr. Aruna, for giving my introducing me. And also I have a small corrections. My H index by Scopus is 34, not 60. It's probably Google this gives a large value, but it's fine. Let me share the screen. Is that seen? Can you see it?
Yes, sir, it is visible. It is actually in the file mode, not in the presentation mode, sir.
Yeah. Okay.
Yes, sir, it is in the presentation mode now.
Okay. So first, let me thank you also organizers and especially Professor Karthikeyan for inviting me to this important conference, international conference. And I will tell a few things about quantum dots by plasma CBD. It's a different method. So like to see what our achievements are in this field. So my colleagues are student Sirajuddin and my other co-worker Vijayan also is involved in this. But a lot of this work was done in Utrecht University before I came here. So to start with, let me pointer. Yeah. To start with for introduction, so it took nearly a long time for the very basic idea to come to some production of the solar cells, photovoltaic solar cells. So I'll try to say how the quantum dots or nanomaterials will be used for making solar cells. Now this has taken a long time for this, and now from that it was used mostly for satellites and space applications. Now it has come to the for terrestrial applications, very part of our life. And you can see that India makes 410 gigawatt. Already last year, 63 gigawatts was made by solar PV. So, it's growing. Of course, last year it should have been 120 gigawatt, but because of pandemic, other reasons, it has not reached that level, but it's growing in that direction. The worldwide, actually, it's increasing tremendously, and actually by 2022, 1 terawatt accumulating install has been reached. That's one benchmark has been reached. So solar PV is very part of our life now. It's no more something like for only for the rich and the space applications. It's for general use now. So why it has become general use is that you can see the price of the solar modules falling. It's a learning curve. The beginning it was falling like history. The learning curve was around 24% up to then it has come down almost like 40% for last for 2006 to 2020. It is falling rapidly. So as you can see here, last year it has almost reached 0.2 watt, 0.2 cent, $0.2. Let's actually, yeah, something like per watt. You can see the India also, the price of the auction price of the solar has come down almost to 2 rupees per kilowatt hour. So it's almost is competing with the general from the fossil fuel. Why then also one more thing, it is sustainable, because you can see here it's mostly silicon. More than 90% of all is solar photovoltaics. Solar cells are all made from silicon. The rest of it is like cadmium telluride, CIGS, other materials. But also all this material, silicon is well available, and you can see all the materials needed for solar cells. The key materials are all they are available, large amount. So it's a sustainable supply for the production of silicon photovoltaic. So as you see here, I'm trying to motivate you why we should go for this quantum dot solar cells. So these are all made by crystalline silicon wafers, the aluminum BSA type of wafers that you see in our rooftops, which are there for a long time, and this is reaching modular efficiency around 20%. Then the new one, which is already this has already gone from the production. Mostly production has gone to PERC cells. This will reach saturation about 23%, around 24-25%. Then comes the next one. It's called the silicon heterojunction cells, or the TOPCon cells. They're called passivating contact cell. They are already taking out the market, and they will within 10 years they will also dominate the market. This will reach around 25% modular efficiency. Then you can see, after that, what will come, the back contact cell will come, and this will cover around 26%. It is saturated. After that, you need to go for some new type of cells, either tandem cells, call it tandem cells, or third generation concepts. So that's where I'm trying to come there. Why it is necessary to go to, this is already high efficiency. Why are going there? Region like this. See, these modules, this graph shows, this is already in 2016, already it was told to us, the cell cost is not important thing. It's the other things are important now. Because let's say this one is the saffron color that you see here. These are all module efficiency, the module cost. But the rest of them is called balance of system cost, which is wiring, cabling, all sorts of mechanical installations. All these things, they come like this. India is much better than many other countries, but they are also quite high. You can see that more than 50% is from the balance of system cost. And this is minded 2016. Already price of modules have fallen down quite a lot. So the balance of system cost now is controlling the price of the solar electricity. And to do that, to decrease this balance of system cost, the efficiency has to be high. Then if the efficiency is high, they have a less number of cost on the wiring, cabling, the land, and the mechanical installation cost. Everything will come down. So then only the price will fall down still further. So now the efficiency is more important than cost of making a solar cell. This was actually, but then question is why the efficiency is limited to only 25-26% for the standard cells. this is because of this region, what you can see here in the graph. This is typically how the PN junction is made to make a solar cell. Light comes absorbed by the material. Electron hole pairs are formed. If this energy is more than this energy of light is more than the band gap, is called band gap to absorb the light, then that energy is lost, what's called elastic scattering loss. If it is less than that, the energy, it will pass through the material. So these are all the losses that material has it for the optical losses. And also there will be some recombination of the electron hole pairs. So all these things bring it to what's called a Shockley-Quasar limit, what's called 30% efficiency limit. I call it actually 33%. So that's what you can see in this graph. This is what the Shockley-Quasar limit, that is 33% maximum you can get. For silicon, which has a band gap of 1.1 electron volt, actually maximum efficiency you can get it 29.4%. So the question is, now we are reaching almost there. If the efficiency cannot be increased further, the balance of system cost will not come down, the price will not come down further. So that's the reason why one has to cross this limit to go to third generation concept. There are many of them, different types of concepts are there by which you can go to this sort of third generation concept. This was proposed by Martin Green in 2003, that one has to go towards this sort of concept cells to make high efficiency solar cells so that price will fall down. These are all the thin film concepts like cadmium telluride, CIGS. All these are all thin film technology where the cost is less, but the efficiency is lower than crystalline silicon. So here this cartoon shows the meaning of efficiency. See, Martin Green showed that if you make tandem cells like two cells connected to each other, let's say you have a amorphous silicon and silicon germanium, for example, like that. So if you increase the number of two cells in tandem, it will go from this 33% efficiency to 45, or for silicon, it will go from 29% now Shockley-Quasar limit. You can go up to 42.5% efficiency with a crystalline silicon in addition to another cell, like let's say perovskite top cell. So the more the number of cells, if the 2 or 3 cells are connected in series, you can keep on increasing the efficiency. It's called tandem concepts. But there are other third generation concept, and Oxford made a calculation that if you reduce the cost of the cell, for example, by 20%, the saving amount of saving and the cost saving only 3% only. But if you increase the efficiency by 20%, your cost saving is 17%. You can see the importance of that. Cost of the solar cell is not important anymore. If somebody says that I have got a cheap cell by some method, that's not so important now anymore. It's the efficiency that is important. Even if it's more expensive cell, the efficiency is more important there because of balance of system. So that with that concept, we are going towards this third generation concept. As I said, that first generation concept like silicon have reached already 26.7%. Actually, it has gone to 26.8% recently by LONGi. And gallium arsenides can go up to 29.1%, but these are all expensive thin film lift-off technique. The second generation concepts are like amorphous silicon 10%, CIGS 23%, cadmium telluride 22%, and the dye-sensitized cell. All are actually moderate efficiencies, and they have the many stability issues also. Then we are going for this third generation concepts, and these are already reached by silicon with 32.7% 5% efficiency, and these 3,5 compound tandem cells have reached to near to 40%. These are mainly used for the space application. That's not for terrestrial. For terrestrial application, already we are going towards more than 30%. Already Shockley-Quasar limit has been crossed. In this matter, out of all these things, we are interested in the quantum dot solar cells, which can go up to more than 30% efficiency. So I'm giving you the examples of the first, second, third generation solar cells, and so this is all from my group from the past, from up to now. So these are basically first generation concepts made from solar cells. It's a typical solar cell of silicon heterojunction solar cells. I'm not going details into that, but they are all crystalline silicon based. But a thin film based solar cells have got many benefits. They can be flexible. This is the stainless steel foil. This is polyimide foil. This can be a large area like Amarth applied materials system, which is very large modules can be made, or roll to roll modules, which are produced, developed in my lab as well as AkzoNobel and a few other partners. So all these things are possible in the thin film case, whereas not possible in the first generation. Whereas third generation concepts are like tandem cells, double tandem, let's say like this, or a triple. These are all made by amorphous materials. Nowadays, we are trying to go towards this crystalline silicon-based tandem cells. You can also have here the up conversion material, which is changing from the long wavelength light to short wavelength light. Let's say unused light of the IR light to the visible light. This is called up conversion cell or intermediate band gap cells. These are the concept of third generation concept. Here we want to use the quantum dots solar cells in this configuration. So this is a proposed solar cell, and we want to have silicon quantum dot top cell and silicon germanium quantum dot bottom cell. There should be a band gap difference. This, let's say, this will be around 1.2 or 1.334 electron volt. This can be 1.78 electron volt, and so the light can come through this, and there is a junction between the two cells. Here, this is quantum dot junctions. The challenge is how to make silicon quantum dots first, then how to make alloy quantum dots, and then you have to make how to make doped quantum dots. All have their own challenges, and this will lead to theoretical efficiency more than 42%. Now in this talk, I will talk about how these quantum dots are made. These two, I will not go further than that. So these are made by what's called cold plasma. You should not confuse with the high temperature plasma, which are for the comets or the Saturn rings, for example. They are all high temperature plasma. So here the plasma is in the equilibrium condition, whereas this is cold plasma, which is non-thermal plasma. All these are actually, the color you can see is because of dust. So the dust is formed in a cold plasma here, and these dusts are converted into nanoparticles. So for example, this is my plasma chamber. So I pass silent hydrogen gas through this shower head, and they will go inside it and they will discharge. And my substrate is here, and they'll go and deposit there. So if I produce silicon quantum dots here, they can be produced. They can be accumulated here. I can see my plasma through my optical emission spectroscopy from here, and also I can know how much plasma power I'm giving to the system by my current voltage probe. So this is a typical chamber, but how we made it? We made a special chamber for this. This is a typical multi-chamber system to make solar cells, so that each chamber can make a PN intrinsic layer. Let's say one chamber is P layer, P chamber, N chamber, intrinsic chamber. Like that, we can make a PIN cell completely. This is a load lock through which you send a substrate, and the substrate will take by the robot arm to different chambers to make different layers to make a solar cell. So one of the chamber was converted to make it for quantum dot, in which this is where the gas comes in, but substrate is kept a bit distance away, and here is the top electrode, which is a grounded electrode, which is perforated, through which the dust or plasma, the quantum dots are produced, and they are pushed through this to deposit here. They are called triode assembly. And what is happening to the plasma, we can see through our plasma emissions from here, and also we can see the plasma current through the BI probe. So this is what oh, it's not coming. Okay, this how. This is where my substrate is. From here, the particles are coming and depositing on the substrate. So here below this plasma is there, through which particles are coming and depositing here. So that is what is happening. The quantum dots are produced here, and they're depositing. How it is happening? So let me explain this one. So I am putting silent hydrogen gas. So this is, let's say, these two electrodes are there. This is RF electrode. This is a grounded electrode. So these are the minus and positive and negative ions are formed here. The negative ions are basically trapped inside because both the electrodes are more negative compared to the plasma bulk. So negative charge cannot go to they will be trapped here, whereas they will be bombarded by the positive ions. They will go and bombard there. And of course, neutrals also are going depositing. Now, what happens that this negative charge, SiS3, for example, minus, they will, once they're inside it, they will interact with another silane. So they'll produce S2, Si2, S2, H5 minus. Si2, H5 minus again will react with silane. It will keep on increasing and they'll become a cluster. And this cluster will still be trapped unless it reacts with another positive ions, then they'll become neutral and go to the wall. That means it will go to the substrate. But it can also pick up another electron here, still get trapped. You can also get neutral reactions like SiH2 radicals, SiH4 also can go on up to become clusters. So what happens? It depends now on the residence time of the gas in the chamber. Residence time depends on the pressure and the volume of my plasma zone and the flow rate of the gas. So if you increase the residence time either by pressure or by volume, if you keep on increasing the residence time of the gas, it will go from a simple radicals formation inside to make amorphous silicon. You become more and more, it will become clusters are formed, like these clusters will form. Then they'll go inside, make a polysilane, they'll become voids inside. If you get slightly bigger, they'll become like a small nano clusters. They'll get into the material. It's called polymorphous material. Or still bigger than that, maybe 1 to 4 nanometer of size of these ones. If they're called nano dots or quantum dots, they can go to the substrate and deposit. If you give it bigger than that, they will coagulate and finally they become dusty plasma. And this is not what you want. Normally it should be removed. So whole idea is that before it goes there, you have to pull it away and make a deposition of the quantum dots. This is how it is done. If you look at the plasma, they look like this. This is the grounded electrode and the RF electrode. So this is coming from the sheath area with this because of discharge here. You can see the color here, and this is non-dusty plasma. So there is no dust here. But you can dust plasma. You can see it's more homogeneous light with heavy light in between, and this is basically coming to the dusty regime. And there will be dust to be like this. These are all quantum dots size, but these are all really clusters, very dusty regime. So maybe so we have to find that this is dust-free regime. This is good for amorphous silicon materials, but if you want to make quantum dots, you have to be somewhere here to make a dusty regime. It's called gamma prime regime or a dusty regime. So how are the particles collected then? So this is how you can see them. This is a plasma bulk. Let's say the particles are formed here. So there are two things happening. The particles are negatively charged. So they're trapped inside. They're trapped inside by the electrostatic force, which depends on the radius of the particle, which is allowing the particles to be inside it. So that is called trapping force. This is trapping it. The de-trapping is that the particles can get out from the plasma zone and deposit both sides. So there is one called ion drag force, by which one ion, a positive ion, for example, is coming there and it's pushing the negative ion, which are the particles, dust particles, and they're dragging along with them. This is called ion drag force, which depends on the square of the size of the particle. It's a neutral drag force. For example, here is the pump. So the gas is flowing like this. The gas is neutrally dragging the particle. That's called neutral drag force. That also is proportional to the radius of the square of the radius of the particle. Then there's called thermophoresis detrapping force. That is, if there is a temperature difference between the plasma bulk and the ground, there is a temperature gradient. It pushes the particle from one side. It's called thermophoresis. And fourth is the gravity. Gravity will bring it down. So you can see here in this one, you can see here. So this is gravity will fall down, everything is coming this side, whereas the ion drags will go from both sides, whereas neutral will go only one side will go, and thermophoresis can be from both sides. So this one and this one will allow for particles to be deposited here. So as you can see here, the small particles, if the size of the particle, this force is much bigger than this, so they will be trapped. If the size becomes bigger and bigger, the detrapping force is bigger than trapping force. The particles go towards the escape from the plasma zone and deposit on the wall. That means deposit on the grounded substrate. This is what we do. So that means at some size of the particle, it will come out from the plasma zone. And this is an example of a ion drag force. This is a particle is inside it, the quantum dot, let's say, and there is another ion, positive ion is coming here. If it's within this Debye length inside it, so it will just push this one to the grounded electrode. It's called ion drag. So what happens is that I just said that particles will form. They become some size will form. Once the one size is reached, it will go to the wall. Again, another new particle will form. Again, the size becomes bigger and bigger. Once the R value becomes some size, it will get out from the plasma zone. It becomes like the breathing. It's like a breathing. It forms, detraps. It goes on like this. So you can see him like this. This is first this is, let's say, the plasma zone. This is the two walls. The plasma zone. First, the particles are formed. Then at some time the particle size becomes bigger because of the R square. They'll become bigger. They'll go to the wall. Again, new particles will form. Again, it'll go to wall. So it goes with a frequency. You can see this frequency through the optical emission spectroscopy. The light, plasma light, also will go with some frequency. Also, the plasma current will go to frequency. If you take the first Fourier transform of the plasma fluctuation, either from OES or from the plasma current, you'll see that there is a peak first Fourier transform peak, which is coming somewhere. Let's say that means around 40 hertz. These particles are formed, detrapped, again formed, and detrapped. And also it's a line frequency because there's 50 hertz line frequencies here. So this is how the frequency at which the particles are formed inside and detrapped. So, and this frequency basically depends on the two things, the total flow rate and the temperature of the gas temperature. This has been well documented by us. Now what happens if one more thing also I can see that if I use only silent hydrogen in the gas phase, I get big particles. But if the hydrogen concentration goes up, you can see the particle size comes down and down. This is very big size. We don't want. It has to be smaller than 5 nanometer. So you go somewhere above this 100 H2, the more hydrogen, then you get small size particles. That's called quantum dots. So one more thing also is there that I just showed you this how the particles are coming out from the plasma bulk. This is where the particles are formed, and they're coming out from the plasma bulk and depositing here. There are two types of plasma is actually created. One is a bulk plasma. One is here. For example, this is this one here. This perforated the ground electrode. Here, there's an intense plasma is created. These are two different plasma. So from here, the plasma bulk, this will come as this one here. This small spots where the samples are formed here. Whereas this one, from the groups, they go in a conic in a divergent way. So that forms like big ones. Mostly the big ones are amorphous, and whereas this one is mostly crystalline. And you can see them. So the spot one, that is this spot, the small ones, they are basically crystalline. You can see them also from the TEM picture and the first Fourier transform of them. You can see them; they're all crystalline.
Professor, you have 10 more minutes, sir.
Yeah. I started 1:10.
Okay, then 15 minutes. Okay. So.
Yeah. So as you can see from spot 2, they're all amorphous like that. And we have particle distribution. You can see them. The small particles are around 2 nanometer. These are all quantum dots. And what you can see that the residence time determines the particle crystalline size, crystalline ratio of the material. Those particles which are formed, how much crystallinity is there depends on residence time of the gas. The residence time can be changed either by the plasma volume or by the gas flow. So this way we can control the crystallinity of those particles. The second method that is used called pulsed plasma. You pulse the plasma. That means what you do that you don't have one continuous plasma. This is all very frequency plasma. There's a 50, 60 megahertz. But what is that? You pulse it. Pulse it means you are on it for some time, then off it, then on it, off it. This on time will tell you the growth of the particle. That particle will start growing up to that one, and after that the particle will be collected by the substrate. Then again is plasma is up. Then again particles start formation. So you can from this The on period, you can control the size of the particle. And off period will allow you the particles to get out from the system, also the flush of the chamber. And I can show you this one. You can see them is pulsing. So it's all pulsing. So this way, what happened that is, if you have to keep the off time more than the residence time of the gas. If the off time is less than residence time of gas, what happens that not all the particles are removed from the system. Those particles will remain in the plasma zone. Will start growing. So you get different types of particles inside it. Whereas if the off time is less than the residence time of the gas, you get the homogeneous monodispersive particles here. So that's what is basically written down here. And there are different phases by which the particles grow. The first particles grow as small particles. Then at longer time, the particles start coagulating and becomes like cauliflower structures afterwards. But these are all quantum dots still, because their sizes of particles are less than 5 nanometer. And these particles are actually conducting. If you look at the tapping mode, these particles, we did the conducting mode. They are all conducting. So these particles are real crystalline particles, and they can be used in solar cells. So we have been successful making the silicon quantum dot. And why the quantum dot is formed is that in the gas phase, because this has been a debate for a long time. One can understand how the nanocrystals formed on the surface, but how it is formed the gas phase. So this is just dust particles. You can get from various sources. Energy can be transferred to the dust, which is primarily beginning amorphous cluster, and they will gain energy by different processes. These blue ones are by which they lose energy. For example, if it is the hydrogen recombination reaction on the surface, then it will gain energy. Etching also, abstraction also, they will gain energy. This energy, if it's more than what is necessary for crystallization, they'll convert it to crystals. And basically, the change of the temperature of this one given by this equation, and this is all generation of the energy, and this is loss of energy, and it will give you rate of change of the temperature. The temperature is high enough, they'll convert it to crystal. So that's why the crystalline quantum dots are formed in the gas phase itself. And this, okay. But then when you go to start making silicon germanium quantum dot, then you have problem. Because of the mismatch between silicon and germanium lattice mismatch, it will not allow, they'll segregate. And there is a difference in the melting temperature of the silicon and germanium. And there is a phase segregation that takes place. These are all calculated. And then germanium tends to diffuse out of the system in order to minimize the cost of dangling bond. The dangling bond costs a lot of energy, and so that also it want to save the energy. So it's normally it has been proposed that silicon germanium or any sorts of alloy is difficult to make in the gas phase. But we did that. We used silicon, silane, German, and hydrogen gas with argon, and we started making these particles. And from this XRD and the Raman, we found the particle sizes. And this particle size, not only particle size, but also the germanium concentration in those particles can be controlled by using a German to silane ratio in the gas phase. We can make different amount of germanium into the system. This has been controlled very nicely, so we can control how much German can be in the particle. And not only that, but also at any silane to German ratio, we found that the germanium to silicon concentration remains constant. That means homogeneous quantum dots are produced throughout. And not only that, but they are mixed up. You can see them. At any place, they are all mixed up. This both silicon, germanium, they're everywhere. So germanium fraction, if you do pulsed plasma also, similarly, we could change the concentration of German in the quantum dots gradually by changing the German to silane ratio. So not only continuous mode, but also in pulsed mode, we can vary nicely germanium to silicon concentration. Just last few minutes, I'll tell that I'll just go somewhere. Yeah, I think, yeah. Yeah, so what we saw that we wanted to see the band gap of this material, and this silicon germanium quantum dots, if we use conducting AFM and find out the current and voltage, we found out the band gaps to be around 1.8 electron volt, and this seems to be n-type. However, if you use scanning tunneling microscopy, we found that it's more of a p-type, slightly p-type, and the band gap is around 1 electron volt for this one particular type of material. So this is why then it is n-type in the when you do conducting AFM, and p-type when it comes to the scanning electron scanning tunneling microscopy. The two methods giving different values. We think that conducting AFM we do, it's touching on the top of the oxide layer. It's giving n-type nature, and also band gap is high. Whereas the tunneling scanning tunneling microscopy, it gives only from the particle directly. So that gives you a lower band gap and also a slightly p-type character. And we measured the bulk silicon germanium band gap. What could be if you take that much germanium content, it should be around 0.75 electron volt. But with our measurement from the STS, it gives to 1 electron volt. That means it has got this increase must be from the quantum dot nature. That's because of quantum dot nature of the optical band gap increase. So in conclusion, silicon and silicon germanium and quantum dots have been synthesized in the very high frequency CVD reactor. Good process control and particle size is measured by the TEM in accordance to quantum dots. Silicon germanium values of is lower compared to the R value. That's what we put silent to German ratio. You don't get similar ratio, but slightly different ratio you get them. But what's the most important thing that the band gap is shows that is the quantum confinement effect, and they are all quantum dots. You must realize that the quantum dot of silicon is only 5 nanometer, germanium is 24 nanometer. So that if silicon germanium can be easily made quantum dot, because even if it's bigger size, it's smaller than the Bohr radius of silicon germanium. So that's why the quantum confinement effect comes in silicon germanium alloys, nanoparticles, even there are bigger sizes. So this is my group, and I thank you, my group and the DST project. So we are in the process of making silicon germanium and silicon-based quantum dot tandem cells. Thank you very much.
Thank you, Professor, for a very nice and informative talk. You have touched upon the various generation of solar cells. You have given an overview of those things, and also the work that has been carried out in our laboratory. So now the talk is open for discussion. Any questions, please unmute and please pose your questions. Any questions?
Since it's a webinar, those who are having questions, they can put it in the chat box.
Yes. Yeah. Okay. Please join me in thanking Professor Jatindra for a wonderful talk. Thank you, sir.
Thank you. It's my pleasure.
Thank you very much. Thank you very much. So the next keynote lecture will be delivered by Professor R. Jaivel from Alakappa College of Technology, Anna University, Chennai. He will be presenting his research on two-dimensional nanocomposite functional materials for sustainable energy storage applications. I will just read out his short biodata. Professor Jaivel is Dean of AC Tech Campus, Anna University, having more than 31 years of research experience in material science and nanotechnology. He has been designated as highly cited author by Royal Society of Chemistry. His research papers have an H index of 53, and he has published about 470 research papers and more than 10,600 citations. And he has traveled worldwide, and he has He has been awarded with several awards and fellowship. So due to lack of time, I will not go into the many recognitions and awards that he has received. We are very fortunate to have such a esteemed speaker and really a proficient, prolific researcher like Dr. Jaivel. So I request you, sir, to kindly deliver your lecture.
Thank you. Thank you so much for the very exhaustive introduction. And let me just share my PPT. Is it visible now?
Yes, sir. Yes, sir. Visible, sir.
Okay. Yeah. At the outset, I would like to thank the organizers for inviting me, and in fact, I'm very grateful to the SRM and also the organizers, because I have been a speaker for all successive ICONN's conference organized at SRM in the past. So today I'll be talking on the two-dimensional nanocomposite functional materials for sustainable energy storage applications. When it comes to energy storage, we are all very familiar with this kind of small-scale energy storage batteries, or that's 2-volt batteries, which we use in regular gadgets, electronic gadgets. But now that energy storage has become very massive on industrial scale, to meet with the requirement in terms of large scale production of power by different means, and then the storage has become very important for sustainability. And when it comes to the green energy storage, then still there are a lot of options open for this concept of green energy storage, which can be directly integrated with renewable energy sources like solar or wind, and which is also one of the requirements of Sustainable Development Goals of United States. It addresses with the SDG 7 for the sustainability of energy requirement. So when it comes to the Indian scenario, in fact, we have reached the target of 500 gigawatt of energy production very well in advance, almost 9 years before the deadline, which was predicted in 2012. Sometimes, but the target which was fixed in 2030 has been achieved in 21 itself. So the next requirement is how to use this energy judicially and then use it for sustainable usage. So that is what we go for, the energy storage systems in all aspects, whether it's a battery or different kinds of energy storage system. So this talk, I will be giving some brief introduction about the 2D layered materials, which is those who are not very familiar with the material will get to know the details of these materials. Then I would just discuss something about the existing energy storage systems and future requirements. Then move on to the material specific with respect to our research on graphene metal oxide nanocomposites. And we have also been working on the large scale graphene material. We prepare in large scale dimensions, and which is called graphene bucky paper. And where we have also done some fabricated some functional devices and then finally supplies. So when it comes to 2D materials, it was known from the existence of graphene, which is the core material. But now we have wide options for this category. We have different kinds of transition metal dichalcogenides, hexagonal boron nitride, molybdenum disulfide, molybdenum diselenide, tungsten selenide, tungsten sulfide, etc. And this is another group of materials under the 2D layered material category. Then we have different kinds of silicene, germany, or enzene. These are all another group of family of materials. They have a lot of options for this. Then if you take black phosphorus or carbon black or DLC, diamond-like carbon, these are also now categorized under this 2D layered materials category. And the uniqueness of these materials are like, it can be isolated single atomic layer, and where the thickness is of the order of few angstrom in it, which is already the sub-nanometer scale material. And when we have this kind of materials isolated in atomic scale, there are different kinds of opportunities to work on this, like mostly covering the structural engineering part and with the defect engineering. Because if you take a single bulk material, where the even low dimensional defects like dislocations, spine defects, or line defects will have a very high influence on the properties. But when it comes to this kind of atomic scale structures, the defect engineering is one of the primary requirements to optimize so that the materials can be eventually useful for various applications. And when we have the stacking of layers, then we talk about the heterostructures and then the interlayer engineering, or different kinds of porous structure, optimization or tuning of porous structure, then doping of these materials with the different heteroatoms kind of thing. So all these are some of the important topics that people across the world is concentrating on this. Another interesting aspect of these materials are these are all highly multifunctional. For example, if you take hexagonal boronate, it is a perfect insulator with energy gap of more than 5 electron volt. And molybdenum sulfide, selenide, these are all perfect semiconductors with energy gap of 1 to 2 electron volt. And materials like chromium oxide, chromium sulfide, they are half metallic. Materials like graphene with zero band gap energy is semi-metal, and metals like materials like vanadium oxide, vanadium sulfide, these are all metallic, and some materials will have very extreme conductivity, and those materials are called superconductors. So when you look into the absorption range of these materials, it covers the entire electromagnetic spectrum, ranging from UV to visible, NIR, mid-IR, far IR, terahertz, and microwave frequency ranges. So because of this multifunctionality, there are a lot of applications, including communication, digital and analog circuits, interconnects, memory, and sensor applications. And if you take sensor alone, we have different kinds of sensors like electrochemical sensors, fluorescence sensors, colorimetric sensor, photoelectrochemical, electroluminescence, and field effect transition sensors. These are all some of the high-end sensors fabricated using 2D materials. And because of the flexibility, we have different options of having the transparent conductors, flexible touch sensors, wearable touch sensors, plenty of applications. And in electronics, these materials play a very major role in extending the VLSI technology, very large scale integration to ultra large scale, also to extremely large scale integration devices, where material, millions and millions of transistors can be integrated in a single chip. And biomedical applications include diagnostic, therapeutic, biosensing, bioimaging, and also to some extent, these materials are useful for biosafety also. And there are a lot of applications in photonics. And now if we integrate these 2D materials with 3-dimensional nanostructures, this becomes what is called 2.5D materials. For example, if you take graphene as a layered, bilayer graphene, and then intercalate with 3-dimensional bulk, and this becomes 2.5D materials. All these materials can be converted into 2.5D. By properly integrating with the 3-dimensional structures. There are a lot of interesting phenomena and also application potential for this material to be useful for various applications. So this is also another interesting area where a lot of people are working on this integration of 2D materials and then 3D materials with 2D nanostructures to make it more efficient for very specific requirements and applications. Okay, well, this is a well-known 2D material. As I said, the graphene is the core material, which was known for almost 2 decades now, and they got the Nobel Prize in Physics in 2010. And the application potential involves, we have graphene electronics, lithium-ion battery, photocatalysis, supercapacitors, and people have also demonstrated organic light emitting diodes using this. Recently, the graphene oxide, even before it is converted into graphene, the graphene oxide has a very strong antiviral and antibacterial activity. And there was a very specific requirement in terms of graphene oxide coating on face masks or personal protection equipment, especially for protection from COVID-19. Okay. So we have been in our laboratory, we have been working on 4 verticals. One is on graphene-based FET sensors, and this is not a conventional gas sensor or biosensor or chemical sensor, which are all used for high-end applications like DNA hybridization sensing, C-reactive protein sensing, high-energy radiation sensing, and sensing of NBC, nuclear, biological, and chemical weapons. Those kind of applications are there. And coming to the photocatalysis, we have been extensively working on this because of the advantage, like these materials can have a very large surface area of about close to 3,000 meters per gram. And we have also been working on graphene integrated 2D integrated with zero-dimensional quantum dot structures. As the previous speaker also discussed about the quantum dot based solar cells. And the advantages, for example, if you have this kind of graphene integrated cadmium sulfate cascade layers, it has been theoretically predicted the amount of photoelectrons absorbed on the surface of 10 square centimeter area is almost equal to 1 square meter area of conventional silicon panels. So because the silicon technology is the mature technology, but the only difficulty was the space. Like, when you wanted to harvest 1 kilowatt of energy, you have to have 1 meter square size of panels. But there is a large scale miniaturization possible with this kind of structures. So we have made some quantum dot sensitized graphene solar cells, and also we made heterojunction solar cells by this kind of techniques. Then this is the energy storage applications. We have been extensively working on this, mostly for supercapacitor applications with reasonably good amount of energy density and also very high power density requirement for high-end applications. Okay, so coming to the energy storage systems, we are all very familiar with this. We have the two-wheelers, which are basically based on lithium-ion batteries, and the performance and the cost also depends on the power of the battery. In e-bikes or two-wheeler, then we have three-wheeler, four-wheeler, and we have then even passenger vehicles are also now operated through these batteries. And the very well-known battery which has been used for all these electric vehicles today is lithium-ion battery, which was discovered in 1970s and commercialized by Sony Corporation in 1991. And this great discovery was recognized with Nobel Prize in Chemistry in 2019. And if you look into the 2019 data, there are about 7 billion units of lithium-ion batteries manufactured across the world. But now this recent data is about 12 billion units of these batteries, and mostly from Asia Pacific regions, because we have a large-scale manufacturing facility in China, followed by North America, South America. Europe also has now a lot of manufacturing units for that, and Middle East and South Africa, Africa. Globally, there are a lot of developments happening for the lithium-ion batteries. But when it comes to the Indian requirement, the government of India and also the state government has brought out the electric vehicle policies with the target of replacing almost 100% private transportation to be battery-based by 2030, and at least 75% of the public transportation should be based on these things. But the major difficulty is the cost factor, right? So when we look into the data presented in the Parliament in 2020, there is a steep increase in the export of lithium-ion batteries from 2016-17 to 18-19. Afterwards, there was a decline because of the exorbitant imported cost for these lithium-ion batteries. And the government has took initiatives to what is called develop the indigenous development of lithium-ion batteries, and then this was actually an MOU between the SECRI, Central Electrochemical Research Institute, Karaikudi, and this is with the Rasi Solar, a Bangalore-based company, They have been in this field for many years to develop the lithium-ion batteries. And then Indian Oil Corporation has independently developed indigenous metal-based batteries for EV ambitions, and ISRO was to supply lithium-ion battery technology to, especially for the automobile sector. And apart from that, we have a lot of startups focusing on electric vehicle motors, charging stations, and then other peripheral devices. But there are a lot of efforts both from the government side as well as public sector, private partners to develop this. And one important thing is like when you come to the look into the lithium source available in different regions, India is nowhere. And until last month, we were very poor in lithium resources. But it all came in news also that there was a huge source available now discovered in Jammu Kashmir. It is almost going to be around 5.9 tons of lithium source available now. So this kind of indigenization efforts will be very successful in future. But as of now, countries like Australia, Chile, China, they are the most abundant in lithium sources. So therefore, the entire world gets this lithium source only from these 4 countries, including Argentina, Brazil, the South American countries. Well, whether looking into the alternate, because of the, even if you have the indigenous development, that our lithium source is very limited. So people are also looking on alternate battery materials, looking at various options like transition metal oxides, layered materials. This is actually the 2D based materials, then transition metal chalcogenides, carbon-based materials, and different kinds of alloys, phosphates and polynoids. These are all different options. People are looking into that as an alternate to lithium-ion batteries. And fluoride-ion batteries also a potential material, and it has been predicted that there will be almost 10 times more energy density for this lithium compared to lithium batteries for fluoride-ion batteries. And this is actually iron-based batteries, and this is air-based batteries. So all these batteries are now possible that some of them are already commercially available. But when it comes to the large scale production, lithium is still dominating, but there are options are like sodium and sulfur based batteries are also going to be the replacement feature in lithium ion batteries, considering that cost and other factors. Okay, so in some places like recently in Switzerland, and there was some restriction in use of the electric vehicles because of the power requirement for charging the batteries. Okay, so in fact they have very severe power crisis because of the for the Russian-Ukraine war, and therefore they decided to ban the EVs because the domestic requirement is very much affected because of the continuous charging of these batteries. So as an alternative to batteries, the best option would be to go for supercapacitors, where we can get a very high storage capacity in terms of energy density, and also it is very useful having a very high power density in order to operate the heavy vehicles with a very reasonably high speed. So the supercapacitors, which is expected to have the very high energy density and power density, can meet the high-end requirements in terms of energy storage. And the supercapacitors are known for almost now 3 decades. In 1995, the Russia first started the supercapacitors to power the electric cars. And then very fast charging station has been included in 2004 and 2006 itself. The commercial vehicle was launched based on the supercapacitors in China, and supercapacitors, heavy electric vehicles were also introduced. Now that flexible supercapacitors, because of the materials like the 2D materials and other flexible materials, we have the flexible supercapacitors. Now the rechargeable supercapacitors are also now coming up. So that means that the utility and sustainability can be very much assured with this kind of development of supercapacitors for future requirements. And the very basic applications, it was started with supercapacitor, was mostly the memory backup and instantaneous power requirement. But now that has been scaled up to meet with this kind of grid storage, which can be integrated with the renewable energy sources like solar, so that large scale grid storage can be possible with this kind of supercapacitors. And of course, the high-speed vehicles like SUVs or this kind of high-speed trains can also be operated using these supercapacitors. So another future requirement is that supercapacitors for aerospace and defense application is the most important because of the cost involved in other sources of energy storage. And supercapacitor for generation next high-speed trains, which is also the potential option to go for supercapacitors because of its a very long cyclic stability lifespan when we compare to the batteries and other things. Okay, these are all some of the areas that has been developed in a very comprehensive way where the usage of supercapacitors. So when it comes to the materials options, like we have different kinds of materials options like transition metal oxides, metal sulfogenides, then black phosphorus, MOFs, metal nitrides, and then new kind of materials are being evolved and to address the requirement. Then the electrolyte is also another important component which has to be optimized for sustainability. And the storage in terms of its energy density, power density, and also the miniaturization or cell designs, which are also now taken into consideration when it comes to the high-end applications. And future challenges are also now there because the wearable and smart electronics are also integrated with the supercapacitors to be useful for various applications. So coming to the materials aspects, most of the carbon-based materials like activated carbon, carbon aerosols, carbon nanotubes, including graphene, which are all potential material for supercapacitors, and different kinds of polymers like conducting polymers are also possible. And metal oxides are known for their efficient energy storage with the supercapacitor mechanism. And we have tin oxide, manganese oxide, zinc oxide, titanium oxide, ruthenium oxide. All these materials are having the potential to be useful for energy storage, where the specific capacitance can be achieved almost 800 farad per gram. But the combination of these two, like metal oxides and carbon-based materials like activated carbon or CNT, carbon black, and so this kind of composite hybrid structures increases the specific capacitance almost 1,200 farad per gram commercially for optimum thing. But individually, the cell, the electrodes can reach almost even 2,000 farad per gram. Okay, so in terms of energy density, specific capacitance. So other kind of materials other than the metal oxides or polymers or carbon-based materials, metal halide, perovskite oxides are also useful for energy storage applications. Not only for energy storage, it's also useful for energy conversion process. There are a lot of activities going on in this. And this is actually the process optimization, which involves multiple parameters for optimization to achieve the better cell performance, including the power density, energy density, maximum operatable energy density, power density, and other kind of parameters. Okay, graphene, the advantage is like the graphene has a very large surface area, as I told you about, which can have almost 3,000 meters square per gram. And because of this, a lot of requirement in terms of graphene-based structures. Other advantages that the graphene can be synthesized by a variety of techniques, like mechanical exfoliation, thermal exfoliation, liquid exfoliation kind of thing, CVD, chemical reduction process, electrochemical synthesis. All these methods are available for graphene synthesis. And in fact, the synthesis methods can be categorized based on the application aspects. For example, if you are using for sensors, the most appropriate technique is to go for liquid phase exfoliation. And if it is for high-end applications, we can do the chemical reduction or chemical for supercapacitor solar cells. Mostly the chemical reduction process are used. And this is actually the simple chemical reduction process by which this graphene oxides can be prepared and then converted into graphene or reduced graphene oxide. We take the natural graphite as the source material and then mix with the very strong acids. And then we can deliberately introduce the oxygen functional group by adding oxidizing agent to introduce the oxygen functional group. And then after filtering and washing, we can dry it at vacuum to get this graphene oxide. And the graphene oxide can be mixed with water, and after sonication for about 1 hour, we get the graphene oxide dispersion. To reduce this graphene oxide dispersion, then we use proper reducing agent. Here we have used thiourea as the reducing agent. Reflects it at 95 degrees Celsius for 12 hours, you get the reduced graphene oxide. If you are able to reduce all the oxygen functional group reduction in the matrix, then we can call it as the graphene. But the chemical reduction process, there is always a skeletal residual oxygen functional groups which are present in the matrix. Therefore, we safely call it as reduced graphene oxide. So this is another technique called solothermal technique, which is also useful for graphene synthesis, and many people have used that one. So once you prepare the graphene, there are three major fundamental studies will be used to FTER to check the extent of reduction. Right here we have different kinds of oxygen functional groups like carboxyl, hydroxyl, carbonyl, and epoxyl groups. And if you are able to reduce all the oxygen functional group, then it becomes graphene oxide. But many a time, we have some residual oxygen functional group. Therefore, we call it as RGO. And this is the Raman, which shows that we have the D and G band peaks. And sometimes, if we have a stacking of few layers, then we also get the overtones 2D and D plus G peaks at the higher number rate. And this is the thermal stability. For example, if you look into the TGA, the RGO is stable only up to 200 degrees Celsius, and it's almost 40-60% weight loss happening here compared to GO. GO is stable only up to 200 degrees Celsius. It's almost 100% weight loss. So there is a very huge difference between the GO and RGO in terms of thermal stability. This is actually a stacked layer of graphene, and this is an isolated layer. And then we can also check the crystallographic orientation by FFT, fast Fourier transform image of TEM. These are the very basic conformations of this formation of materials. But when it comes to, there are different kinds of applications, but as a result, we are more on energy storage. Then we do the cyclic voltammetry of this one. And if you look into the cyclic voltammetry of pure graphene oxide and RGO, and there is almost double the time of the current value, going from 800 microampere to 1600 microampere. And the specific capacitance for this kind of electrode is about 800 farad per gram, and which shows that the material can have a very high energy density, but the power density is limited because of the low current value. And therefore, we tried with different composite structures with tin oxide composite, where we could get current of the order of milliampere range from microampere. And then these are all actually the confirmation of distribution of tin oxide. And for some reasons, we deliberately coated the PMMA polymer coating on this, and which has also reflected very clearly in the FFT images of this electrode. And having got the milliampere, but still we wanted to increase to the ampere range. Therefore, we tried with the different options. This is actually RGO with cobalt oxide, and the cobalt oxide has the tendency to form different combinations, like spherical particles and kind of trigonal and some kind of clusters. And in all these forms, that cobalt oxide is combined with RGO, and we get the current density of the order of milliampere. And for this electrode, the power density was estimated to be around 285 watt/kg, and then with the energy density of 44 watt/kg. And the cyclic stability is also reasonably good, up to 2000 charge discharge cycles at an current value of 10 ampere per gram, which is 96.6%.
Professor,
These
you
are
have
discussing-
another 15 minutes.
Yeah. 15 minutes?
Yeah.
Okay, fine. So this is actually the RGO, ruthenium oxide RGO composite. As I told, ruthenium oxide is a stable binary oxide where we can prepare these materials in a very high pure form and then integrated with the graphene oxide. And if you just see the current density for ruthenium oxide graphene composite is also reasonably good, and the energy density and power density was measured for this. For example, graphene oxide is this one. Ruthenium oxide binary metal oxide itself is having an energy density of this value, and the combination of these two have the maximum energy density and also the power density, which is very good in terms of stability also. Okay. So having done this, we also tried with the different metal oxides like titanium oxide, and with this titanium oxide we fabricated a 2 electrode supercapacitor cell and then studied the performance. Here you can just see the current densities of the order of ampere range, which is also good for electrodes. Then this is actually the different kinds of morphology, the bismuth vanadate in one-dimensional structure, so which was integrated with RGO by in situ reduction process. Then you have the random orientation of this bismuth vanadate one-dimensional structures, and this is actually the Raman imaging. And for this kind of electrode also, we have the current density of the order of ampere per gram, and which shows that these electrodes have very high power density. Having done with metal oxides, we also tried with some metal sulfides like cadmium sulfide, RGO, zinc sulfide, lead sulfide, and this kind of very tiny particles were integrated with the two-dimensional matrix. And this is a Raman where you can just see the because of the presence of cadmium, we have different kinds of longitudinal optical phonon mode, first order, second order, and third order things. And this is actually cadmium sulfide pure, and you have the confirmation of D and G peaks. And the another interesting observation is like there is a very strong luminescence quenching when we make a cadmium sulfide RGO composite compared to pure cadmium sulfide, and this is attributed to the very close Fermi energy of the cadmium sulfide and graphene substrate, which is 4.4 electron volt compared to 4.4 electron volt, and also the electron affinity and surface of 2D layered RGO and the cadmium sulfide, which is also another reason for this kind of very strong luminescence quenching. Okay, and when you just look into the current values in the cyclic voltammetry, it also comes out to be in the milliampere range. And we also made some heterostructures, as I said initially, and this is MOS2 RGO2 2D layered stacking done by in hydrothermal process, where you have the graphene, molybdenum, graphene, molybdenum, MOS2 alternate layers. And this kind of electrode is also very highly stable, where we can have the current density of the order of ampere range, the cyclic stability, and also the power density, energy density. This is for graphene oxide, this is for MOS2, and the hybrid structure, combination of MOS2 graphene gives a better energy density and power density. As I said, that the integration of this 2D and zero-dimensional or one-dimensional was possible in terms of different application potential. So we tried to have the three-dimensional cerium oxide integrated with the two-dimensional RGO, and then combined with one-dimensional CNT to make a complex structure like this, and which was also highly stable, where we could get the current density of the order of ampere per gram. And this is the chronopotentiometry and cyclic stability for these structures. So like that, we have tried with different combinations. So like MnO2, CO2, and cobalt oxide with things. And these are all things. Then we also work on the nickel cobaltite based systems, which for the want of time, I'll just skip. This also forms with very good composite with RGO with a highly stable structure, and the rate capability and the specific capacitance values are maximum for this kind of things, like 1800 value. And we also did some work, and actually this is actually a coin type cell fabricated using this nickel cobaltate activated carbon, and then we also made this pouch cell for this kind of things. The power density was also reasonably good with a very high energy density for this kind of electrodes. Then we have done some work on large scale energy density. And the large scale graphene structures, as I told you, this was prepared by Hammer's method, and instead of going for chemical reduction, we have done the inert atmosphere annealing with argon and nitrogen atmosphere to reduce the graphene oxide to RGO. And this was done by in situ self-assembly process, where we take the graphene oxide and mortar it to put it powder, sonicate it for about 1 hour, and then it's poured on a petri dish. And before pouring, then it was coated with silane, so that afterwards formation it was easy to peel off the surface. And then it was just heated at 150 degrees Celsius. Then you get the graphene oxide paper, and this is the self-assembly mechanism by which the formation of this one. And we just did some molecular simulation studies to fix the annealing temperature for the argon and nitrogen atmosphere. So the optimization conditions were like 450 to 500 degrees Celsius, but 500 degree, that kind of fragmentation takes place. The 450 and 400 was the stable optimum temperature to retain the molecules intact without any physical deterioration. And this was the Raman, which is again doing the DMG back peaks, and this is the actual structure. It's almost 10 square centimeter area with a thickness of about less than 15 micrometer. But we are trying to reduce this to still a level as more flexible. And because of the flexibility, this paper can be, rolled it as a roll, or we can stretch it or bend it. It doesn't lose its stability. So therefore, it was useful to make flexible solid state supercapacitors. And this electrode was tested for CV, where the current is of the order of milliampere with a specific capacitance of almost 550 farad per gram. And if you look into the chronopotentiometry, very symmetric charge discharge curves were observed for this because of the very uniform thickness of the uniform surface, as well as thickness of this graphene paper. So this is actually the graphene paper rolled in a cylindrical form with a polymer separator, which was just connected to the LED to check the charging discharging performance for supercapacitor function. Then the specific capacitance retention was also tested up to 1000 charge discharge cycle for this kind of fabricated device. And we also done some biomorphic electrical actuators using the same configuration of graphene paper separated with two different polymers like PVA H04 as well as PVA Northium solution. And we can just see the very uniform tip displacement for both positive as well as negative bias. And here is actually the device where the sample which is generated. And this kind of flexible actuators are useful for robotic arms, where they can have a 360-degree rotation with very high stability. So this is actually, we done some work on perovskite solar cells also, but we have used this boron doped graphene oxide and graphene paper as a cold transport layer for this perovskite structure. That was also very good. And recently we have done some work on graphitic carbon fiber, because carbon fiber is known for its stability and other flexibility. So we have used this one and then tested with the same LED connected through this electrode fabricated using this graphitic carbon. And these are all the actually performance, the specific capacitance, and then chronopotentiometry, charge discharge, and the current density with respect to applied potential. And this is actually the rate capability for these structures. And then the energy density versus current density values with different things. Okay, so let me just summarize that we have been working on the 2D graphene sheets and the graphene metal oxide composites through modified Hammers method. And we tried to improve the electrochemical properties by different kinds of combination of hybrid structures with metal oxides, metal sulfides, and also sometimes the heterostructures of two different 2D materials. And ruthenium oxide metal is known to have their very high electrochemical performance. And when it comes to the multi-layer composites with 3-dimensional, 2-dimensional integrated system, which is also shown to have very promising electrochemical properties for with very high specific capacitance. And the composite structure also shows a very improved cyclic stability and with very high power density and energy density. And the latest work which we have done on graphene bucky paper has been very promising for flexible solid-state supercapacitors and other devices like biometric actuators or perovskite solar cells. Of course, we have also done some work on ammonia vapor sensing using this kind of layered structures. So with this, let me summarize, and I acknowledge our collaborators, Dr. Lokumar Sreta and Ariga from NIMS, Japan, and Professor Ajay Guru from University of Newcastle, Australia. And the PhD students who have done this work is Sanmugam, Tangappan, Nagaraj, Sengotayan, and Selvakumar. We have funding from DST Nano Mission Program, CRB, and MHRD STARS to conduct the work in our laboratory. So I also acknowledge that NIMS Anna University Joint Graduate School Program, where Mr. Sengotayan and Sanmugam, both of them were in NIMS for some time to fabricate some devices, not only for this. And we, as I said, we have made some DNA hybridization sensing. That work was done in collaboration with NIMS Japan. So with this, let me thank all of you for your patience, and I'll be happy if you have any specific questions or clarifications. Thank you very much.
Thank you, Professor Jaivel, for giving an overview of energy storage materials like different types of batteries and supercapacitors, and also explaining different ways of synthesizing these 2D materials and the work carried out in your laboratory pertaining to the supercapacitors and also actuators. It was really very useful and very informative talk. Now the talk is open for discussions. If there are any questions, please, you can share it in the chat box.
Yeah.
Since it is a webinar, I think you can send your questions in the chat. I think one question, it appears. Okay. No, there are no questions, sir. So
Okay.
please join me in thanking Professor Jaivel for giving an excellent talk on 2D materials for energy storage. Thank you very much, sir.
Thank you. Thank you.
Sorry, ma'am. There is one question, ma'am. Sir, Professor, there is one question, sir.
Yeah, please.
Okay, by Subhankar. His question is actually, what is the range of conductivity that you got for geocomposite superconducting material? What can be the applications of this? What is the range of conductivity that you got for geocomposite superconducting material?
Actually, graphene oxide is actually a zero band gap material. Graphene and which conductivity is not as compared to the superconductors where the niobium, selenium, and niobium tin. There were actually the conductivity of 10 power 12 or 10 power 14, which is very extreme value. But graphene oxide is basically a zero band gap material. We call it as only metallic. Okay, the conductivity is not up to the superconductor limit. Okay, so the main application for this graphene oxide or graphene is graphene has the maximum conductivity compared to graphene oxide, but the conductivity is which is required for the energy storage application in terms of reaching a very high power densities are the order of 10 power 6 to 10 power 8, okay, ampere per centimeter square. But the superconductor requirement is much more. Okay. But there are some reports, like theoretically, that when we make a heterostructures with niobium tin or niobium selenide with 2D materials, then that heterostructures can be reached to 10 power, I'm not very sure, 10 power 12 to 10 power 10 to 10 power 12.
Yes, sir.
Yeah.
Sir, one more question. Okay,
Okay.
few more questions. Okay, sir. Can I know the ratio of RGO in the composite, sir, and compared to MOS to RGO? Yes.
Actually, for heterostructure, the stability is contributed both by 2D layers, MOS2 as well as RGO. But for other metal oxide RGO composite, the RGO is about the range of around 10 to 25%, and remaining 75 is metal oxides. And there was another question: what is the best way to modify electrode surface by reduced graphene oxide? Actually, the surface modification can be done by intercalation process. That's what I told about the 2.5D materials also, where you can have a very tiny quantum dots integrated with the graphene oxide or even this kind of metal oxides. If you prepare less than 25 nanometer size, like the tin oxide or zinc oxide, which can very well fit into the honeycomb layer of graphene oxide or graphene, so the surface becomes very smooth with very high surface area. That are the surface modification we can do for that to have the better performance of the electrode. Okay.
Thank you, Professor.
Yeah.
I think there are no other questions then.
Sure.
Yeah, thank you so much, Professor.
Thank you.
Yes, sir. Thank you, sir.
Sure.
I thank the session of this chair, Dr. S.T. Aruna ma'am from CSIR National Aerospace Laboratory, Bangalore, for conducting this session. I thank you, ma'am. And also I thank Professor Jatindra Kumar Rath from IIT Madras and Professor R. Jayavel sir from Anna University, Chennai for their keynote lectures. Thank you so much, Professor.
Yeah. Thank
Dear
you very much,
participants, yes, thank you, ma'am.
organizers. Thank you.
Ma'am. Thank you, ma'am. Thank you, ma'am. Dear participants, the next sessions will be actually continued in the same platform, okay, in the same login. So the next session will be actually organized by Professor Kamala Bharati, sir.
So please unmute yours.
Yes, sir.
Yes, sir.
Good afternoon,
Yes, sir.
everyone. I welcome you all for the keynote talk. This session will be chaired by Professor Parada Nutella. He is a professor at the Department of Electronic Engineering, University of Rome, Tar Vergata, Rome. He's been working on development and applications of chemical biosensors and artificial sensorial systems. He's been working on applications of machine learning to chemical sensors and study of the optical and electronic properties of organic and molecular materials. He has more than 20,000 citations with a H index of 74. So with this short introduction, I welcome Professor Parada to chair the session.
Good morning, good afternoon, actually. And I'm very happy to take the chair of this session. And we are going to listen to keynote talks, to keynote lectures in this session. The first one is Professor Narayana Rao from the University of Hyderabad in India, and he's going to talk about photonic applications. I don't know if we have a slide of the introduction. Okay.
Yeah. Okay, I'm here. Okay. Yes. Thank you, Professor.
Good afternoon.
Good afternoon. Thank you. Good afternoon to all the participants and SRM University faculty. Let me share the screen. Can you see me? Can you see the screen, please?
Yes, it's clear.
Okay, good. Thank you. I will close this one. I wanted these things are okay. This is coming on to the one, right? The side ones are coming.
Sir, we can see the full PPT.
You can see the full screen because I am seeing this, like the side ones. Okay,
we don't see.
Yeah, you don't see it. Okay, good. That's fine. That's nice. Okay. Good afternoon. I'm going to talk today on 1D and 3D photonic crystals and the field enhancement in these materials. For most of I have been a nonlinear optics person for a long period of time, working at University of Hyderabad and SUNY Buffalo, MIT, and UMass Boston. I've been working on the same area and many of the nonlinear optics applications, taking use high power lasers and so on. So, but recently, what has happened is when you come to the applications, what happens? You require your power requirements should be reduced. So that means in the sense, okay, though the femtosecond lasers provides good powers, very now these days, 6 millijoule, 100 femtosecond is very common, or 45 femtoseconds is very common, but the amount of energy that is there is going to be enormous. So one may not be able to use such a powerful system in these materials. So what happens is, so one has to actually come to lower the power. But for decades, people tried to develop new materials which will show higher nonlinearities. See, for example, in the linear optics, the induced polarization is directly proportional to the applied electric field. But once you have, you want to looking at the nonlinear effects, that is when the applied field, where you have in terms of the square of the applied field, cube of the applied field, and so on, it keeps on going, you have any number of terms. But you say, let us say, where, instead of the linear susceptibility, you have a second order susceptibility and third order susceptibility, which are becoming, very important in the nonlinear optics. Of course, the higher terms are available, but these two are the most dominating the terms which play a role. Everybody knows, in the terms of, second harmonic, optical rectification, and three-way mixing, so on, which is even optical parametric oscillators. So they're all popular with your second term, the second order susceptibility. Okay. So now the third order susceptibility is also very, very important in terms of where you must have seen, optical phase conjugation, optical limiting, and optical nonlinear absorption. So, and then most important term which has played very important role is this term. Suppose here you have, it is E cube, right? Okay, now you look at, I call it as a E squared. Okay, V squared, I convert it into mod E squared, I can take it as a intensity. Okay, and that means, I have, and E, of course, this comes to the, E is as if, it is coming like in the linear polarization term. Okay, so that means whatever is the remaining term, okay, I can call it as a constant. That means N2 high. So this means you have, of course, this is a linear refractive index, and here you have got this term leads to an N2 term, N2I. So that is N0, which is normal linear refractive index, N2I the nonlinear refractive index. So that is what actually plays a very important role. Even, for example, all our Tie sapphire laser, which most of it, which has become popular, is based on simply based on the term your nonlinear refractive index. Okay, actually people accidentally found out that TIE sapphire, like started mode locking when they shook the table, it started mode locking. Okay, so that is the first discovery, accidental discovery of TIE sapphire. Now it is so popular, people know the concept, how it has been mode locking, how it has been generating short pulses. So then they found out that actually it is the second term which is playing role. So that is what actually the term that is going to be I mean that's what your term N to I. So that is nonlinear refractivity. Nonlinear refractive, that means depending on the intensity, your refractive index is going to change. So that means you can create whatever you want. In the sense, you can create a lens. Okay, because you have a Gaussian beam, most of the time, you have a laser beam with a Gaussian shape. Okay, so that means at the center you have got the higher intensity, at the wings you have got the lower intensity. So that means this term actually leads to, I can make it if the N2 is positive or N2 can be negative. If the N2 is positive, you will have a convex lens. Okay, so that means, or I can make a prism. So I mean, depending on the shape of the intensity, the beam control, I can create whatever I want. I can have a convex lens, I can have anything that I want. Okay, so most of your Kerr effect is also based on this principle. Okay, so this is what we're going to do is, now I'm going to concentrate today's talk is on how the third order susceptibility is going to play a role in the material. So since the material is, I mean, more that, as I said in the beginning, so they have, it's almost the materials have been, people tried to look, like during the 1980s, early 80s, late 80s, 90s, people tried to look at large number of materials which will have best susceptibility or ultra fast susceptibility. Okay, which will, no, it's a, because most of the time, like porphyrins, like which are found to be very good with 10 to the power of minus 9 ESU. Okay, there are other materials, people, but some of the materials are very, very good. Even they go up to 10 to the power of minus 5, minus 4, minus 3, even minus 1 also. Okay, so like for example, bacterial rhodopsin, they can go up to even minus 1, but they are very, very slow. Even our eye contains, rhodopsin molecule, which actually the susceptibility, the third susceptibility is very, very high. It's almost like 10 to the power of minus, actually 10 to the power of minus 1. Sometimes it is very highly sensitive. It can go in terms of the units. Okay, so that means, even a small few photon flux can actually saturate our eye and lead to very high third order susceptibility, but that is a very slow process. Okay. But if you are looking at a fast process, it is going to be of the order of 10 to the power of minus 9 ESU, and it will be as fast as, because since it is the electronic response, it is going to be as fast as, few femtoseconds. Okay, so now that means we look at, that means we look at, how that means my goal today is going to be, I want, so because since my material is known, okay, I want to look at how I enhance the field inside the medium, so that I use the low power lasers, okay, confine the light in such a way that I can get very high intensities inside the molecule. Okay, inside the system molecule or inside the whatever is the material that I'm using. So that process, that there for that I'm going to try it. What we have trying to do is we are going to use the photonic crystals for the field enhancement. Okay, so we have been, because of the experimental limitations, we have been working on 1D and 3D photonic crystal systems. Of course, 2D is also very popular. Okay, but we don't have the facility, that we have been confined to mainly 1D and 3D photonic crystals. Okay. And then of course, like we wanted to see, in not only use the one is, we will also going to go and use the surface Plasmon effect for further enhancement in these materials. Okay, now what are the tools to see? Because one, we have to see the tools, how we are going to observe these field enhancements. The field enhancement that we have tagged, see, two observations that we have seen. One is SERA, surface enhanced Raman scattering, and then the nonlinear absorption. These are the two tools that we have been using to see that there is definitely a good field enhancement. What is the order of enhancement that we are going to see? Okay, that's what we have been looking at it. Suppose now I will have, because there are a lot of many, because it's a wide spectrum of people who are working in different area. I will go for the little bit fundamentals into this one, and then we'll go into our results. See, the photonic crystals, like they are beautiful, naturally occurring photonic crystals are there, which are, you have a beautiful butterflies, and then you have a peacock feather, and so on. There are all natural, pebbles, like where you can have natural stones. You can see that they are colored stones, where you can see, if you look at the under a microscope or a high resolution microscope, you will see that, all these things, they have got a beautiful structure, structured in like in a photonic crystal structure. Okay, we'll come to the what is difference between photonic. We'll come to the next few slides. Okay, it's like a crystal structure. Okay, it's almost nanostructure, not nano or micro in the sense. Okay, right. So this is what actually gives the beautiful colors of the butterfly or peacock feathers. You have several, you can see a different type of feather, different colors at different regions. Okay, which now these things, like this is the first, like it's actually it's a, we should give for this area for the development of this area. All the credit goes to Professor Eli Abramovich and Professor Sajiv John, whose first publication appeared in the same journal at the same year and the same volume. Okay, so these are the two. I mean, they're the creative articles which have given insight into the photonic crystals, after which there has been enormous work which went into this region. Okay, this area. So from 1987, people started creating. Okay, how to, because different type of photonic crystal structures. Okay, so now I'll come to this. See, now when we say it's a, you see, like there was, when I was a student, like there was nothing like a solid state physics, optics and so on. It used to be like condensed matter. Today also is again all the areas are merging together, and the photonic crystals is something that is actually merges with your condensed matter, solid state physics with optics. Okay, now if you look at if you look at like in most of the solid state physics people, what a crystal is, which is nothing but a periodic arrangement of atoms or molecules. Okay, so now the crystal, this crystal structure, like because it gives a periodic potential to the electron that is propagating through the medium. Okay, right? So now due to the bad diffraction, okay, from the atoms or the molecules, okay, the electrons are forbidden to propagate in a particular directions. Okay, right? If you have, suppose the lattice potential is very, very deep and strong enough, okay, you will see a complete band gap. That means complete band gap in all different directions. That means the electron propagation will be prohibited in any direction of this crystal. Okay, so that is, for example, you have a semiconductor, you have got a good band gap. So that means electron is not permitted to have in any level within that between the valency band and the conduction band. So this is what you have got, a beautiful band gap in a semiconductor crystal. Okay, which is now you come to the photon. Okay, now see the why, see the now if you want to have the same way, that you have to have a photon should experience the same phenomena of as the electron was experiencing in a crystal. Okay, what is it that is needed? Suppose if you look at the electron, the de Broglie wavelength of the electron is approximately about 0.1 angstrom, approximately. Okay, so if you have 0.1 angstrom, that is what actually it experiences. Now you can see, the electron can see the periodicity of the atoms, how they are placed inside the crystal, right? So whereas in optics, okay, in the wavelength of the visible light is approximately around 500 nanometers. Right, so 500 nanometers in an ordinary crystal, if you see where the lattice space, the spacing between the different atoms is approximately about 1 to 2 angstroms. Right, so a wavelength of 500 nanometer sees as if like it's a continuous medium. It doesn't experience the atoms which are placed 1 angstrom apart from each other. So you cannot have a photonic crystal the same way that you have got, that you see it in a for electron sees in a crystal. So you have to create artificially, because your wavelength is approximately 500 nanometers. So that means there is no way that you can place, some atom is too small. So it means that you have to have a sphere of the order of couple of hundred nanometers placed as far as about few hundred nanometers apart from each other. Okay, so the lattice, the same way, if you want to have a complete band gap, you have to have the same kind of a atomic structure that you had in a semiconductor, right? So you have to have the same kind of a structure arrangement in the case of the spheres. So now you have to, that means, if you want to have a photonic crystal, you should be able to arrange some kind of a spheres or the dielectric material. Okay, because dielectric material is the one where, your light experience, transparency. Okay, right? So you have your light, it will passes through, so that it can get reflected because of the index contrast between the surface, between the sphere and the surroundings medium. Okay, so that means the light can get scattered, okay, refracted, and so on. So many ways are there for the light to go through. So that means you use a dielectric media, okay, or dielectric spheres which are separated from each other with just certain spacings of few hundred nanometers. Then you will experience a photonic crystal. So the analogy is that, that you have got exactly the same analogy that you have got with the photonic crystal and your crystal for the electrons, right? So that is what actually you have the, so that's why it's photonic crystal is an artificially created material. Okay. Now you look at now you can have this kind of arrangement. You can have this periodicity you see is the order of few hundred nanometers, because in the visible wavelength, what we talk about visible wavelength is about a couple of hundred nanometers all the way to 1000, let us say 1000 nanometers. Okay, that is absolutely. So now the periodicity is in one direction, becomes 1D crystal. Okay, periodicity in the 2 dimensions. Okay, it becomes 2D crystal, and periodicity in the 3 dimensions is going to be a 3D photonic crystal. So this is actually the definitions of your 1D, 2D, and 3D crystals. This is the same analogy that I have given. Whatever I have been telling, you can see that you have a silicon crystal where the arrangement of atoms of silicon atoms, whereas here in a 3D photonic crystal, exactly in you have arrangement of spheres with the silicon, poly, anything, any medium, dielectric medium, arranged in a crystalline structure physically. Okay, then it leads to a photonic crystal. So that is what actually one. Okay, now see, actually what becomes the density of states is of course, the density of states depends on, your bulk materials, how the density of states, Fermi-Gödel rule says that, the transition rate is proportional to the difference in the density of states. Okay, so density of states becomes very important, how the density of states, that's why, you have the bulk material or the quantum well, quantum wire or quantum dot, accordingly, you have got the density of states are going to be different. And here coming to here, if you see the electronic band gap, you see you have got a K versus omega. Okay, you can see a complete band gap in all. That means in all directions, that you have got a band gap. So the electronic band gap you have completely. But this is a structure simulated band gap phenomena. If you have arranged the crystal, like a spheres. So, but then this is a photonic band structure. So if you get exactly the same like silicon crystal, if you had arranged these spheres in the same way, which is actually almost becomes very difficult unless manually kept arranged. Okay, but you can have a complete band structure. Okay, well, I will tell you later on. I will show you a picture where like how you get the band gap, how much you can get a band gap. Okay, all right. So now you look at what very important is. Okay, what is very important is when we are looking at the band gap, right? Now, see, this is this is a band gap. Now, look at the band gap. So, what becomes very important, see, now there is these are the different curves. This is this is the band structure for what is permitted levels that are allowed. Okay, or I will define what are these two curves, the upper curve and the lower curve, which we call it, this is called, dielectric one, this is called, air one. Okay. So this, so this in photonic crystal, we call it the air band, and this is called, the dielectric band. Okay. Both of them, this is where, the difference between these two is what we call a photonic band gap, like in your same band gap in your the electronic systems. Okay, right? So this band gap here, if you look at the band gap, what is important here is you look at the velocity, group velocity. Group velocity definition itself is d omega by dk. So here, so this is your d omega by dk here is actually it's nothing but is 0. Okay, right? That means actually the light experiences zero velocity, which is that is group velocity becomes a 0. So that means you have got to, that means a slow light. What is the advantage of light? So that means you have, what it leads to is you have got a beautiful light matter interaction between. So now you can practically, you are freezing the light, okay, so that it can interact with the material much better. Okay, so so naturally the density of photon, density of states at this band, at this band edges, okay, right? Okay, so that means band edges means this is your band edges, like, because this is your delta omega. If I see this is a high energy side, this is my lower energy side. Suppose this is my band gap, right? Okay, so that means both at the lower band gap and the higher band gap of band edge of the band gap, okay, you have got, the group, the density of states is going to increase enormously, because it is rho omega is nothing but 1 over the group velocity. So that is what we get. Now you said, I was telling why the upper band is called the air band and the other band is the electric band, is mainly because if you look at, if you look at the electric field, the confinement of electric field, you will see that there are two dielectric media. See, one, of course, suppose I have got a medium which is nothing, there is no periodic structure, then you do not have this band gap. This band gap, these two A and B will converge into the same point. But the moment you introduce a periodicity, okay, then the degeneracy gets lifted, and you will have you have two separate solutions for your energy equation. Okay, so that means you get, this is the band gap, which is, now you look at the field, where the field is confined. This is a high dielectric medium, this is a low dielectric medium. Okay, now the electric field is confined inside for the top of A. Okay, the electric field is confined within the medium of high dielectric constant medium. Okay, whereas in the other one, it's the electric field is for the lower point of, this is here. Okay, it is in the lower dielectric constant medium. So normally what the nomenclature that we use is, we use a dielectric band edge, and then this is air band mode. Okay, and we call this one as a dielectric mode. That it could be lower dielectric mode. Most of the time it is a lower dielectric constant, but which is normally termed as a air band mode. Okay, that is what it becomes. So now if you look at the density of distribution, you have band edges, you have got a large density of distribution, because most interesting point becomes, like the band edges. Okay, that is where we try to concentrate on see how my light propagation at the edges. Okay, now if you introduce, just imagine if you introduce a defect at the in one of the defects, so you introduce, like within the photonic band gap, you introduce a leaky mode. Okay, that mode actually becomes, like very important. So most of the time we try to introduce the defects and see how my photon density can be concentrated within that particular region. Okay, so that is what actually becomes, the defects, the creating the defect, or the actual defect. Condensed matter physics defects always plays a very major role. It's exactly the same way even in optics. If you have wherever there is a defects are there, okay, that plays a very prominent role, right? Okay, now that is what, this is what actually you try to create a defect in a 1D system or 2D system, where you create an artificial states. Okay, now when I was mentioning it, now yes, we try to see the density of states increases at both band edges. Like you have got the lower band edge or higher band edge, or the dielectric band edge or the air band edge, right? So now we wanted to approach, like you want to enhance it, because we are greedy, right? We want to use the lower and lower light intensities. We don't, you see, at the same time, we want to use a almost like microjoules, nanojoules of a pulse laser, so that we can have the same signals as we can achieve in a bulk system with a few megawatts. Okay, right. So this is, we added, like you introduce a plasmonics into the system, then you have got a plasmonics, and that means you get a metal dielectric photonic crystal. So that means you're not simple dielectric photonic crystals, but you introduce a metal, so you have got a metal dielectric photonic crystal. So what we call a MDPC, metal dielectric photonic crystal. Why the plasmonic? Just to have a brief one onto the plasmonics. Okay, so that we have got, like we have got, the local field, which is very close to the your dielectric medium, gets enhanced. This is the dielectric constant of your metallic sphere is negative. So this is the dielectric constant of the medium, surrounding medium is positive. So which actually this becomes, like you can have arrange it such a way that these two become, depending on choosing the wavelength, I can make that these two become equal, and they become nullify each other, so that the local field becomes very strong. Okay, how strong it becomes, you can look at the me scattering calculations. Okay, where if you have a glass sphere, you will see the local field enhancement as much as 2 to 3 times. Okay, if you have a silver sphere, very close to the silver sphere, you will see the field enhancement of few hundred times. Okay, whereas if you have a dimer and you look at within 2 silver nanospheres, in between the nanospheres, you can field enhancement is could be as much as 10 to the power of 5 times. So that means you whatever the field application, at the local field is going to be very, very large. This is because of your evanescent field. Also, that means evanescent field around your your metallic spheres. So the local field is become, since it's very large, so any molecule or atom kept in between these two spheres is going to experience a huge field, and your power requirements going to reduce. So this is what actually the calculated from me theory calculations, how large enhancement that you can see is almost the SCRS signals, surface enhanced Raman signals, going to be enhancement is as much as 10 to the power of 11 to 12 times. So that means your power requirement is going to be very less. This is what actually our first experiments, like one of the early experiments where we wanted to show. Okay, I mean, because we were working with some of the biological materials, there are a lot of results. This is one of the, I will just constituent, just to have a glimpse. I will go through it. What I will do, I will take up one by one the different concepts, and then see how they have been working. So though we had a lot of other results, I will just show you the simplest ones, where we could place a molecules of inside, this is very, very surprising, because we try to coat in a silica wafer, sorry, a silicon wafer, and then a glass substrate. Glass substrate we have taken like which was available in the market, and tried to see which the one. So because the silicon was very, very well polished, it's like a precise structure. So actually they were when we deposited this silver nano clusters, they were all well separated, and we could not get a good field enhancement. Whereas in a glass, because of the rough surface, we could place the these clusters very nicely. And then their sizes were, so some of them went into the deep, wherever there is a depression, they went inside, and then the other particles we were. So that means, like we could see a much better enhancement when we could use the glass substrate. Excuse me. Yeah. So this is we found, because then we extended, like using the same substrate, we could extend to some of the biological materials. We could go to the concentrations of almost 10 to the power of -11, -12 molar concentration. We could still see the detecting the signal. Okay. And because since we do not know where the placement is, so actually we used a large area beam, so that we don't concentrate, because earlier we were used a confocal microscope, but then we used a change the spot size much larger, so that we could cover the larger area, so that even somewhere, even if the molecule such a at very low concentrations is located randomly at different point, we could still detect. That is one of the very easy way that we could signal. Okay, this is some of the earlier results where I have shown how the enhancement is. Okay, it's a very good enhancement that we have seen. Okay, then we created. And now, since we wanted to have a random structures, actually we did our lab did a lot of. Actually, I'm not going into this one. Okay, but we could laser writing is one of the area that our lab has been working over last almost like 10 years. We can create different structures. We can create a beautiful gratings. We can create a flower kind of a structures. We can create a one. So we can create whatever is the structure that we wanted to create with the laser direct writing. Okay, so the periodic structure comes, if you have exposed few pulses. Okay, so that where the interaction is between the incoming pulse and the surface plasma that is getting generated on the surface. These two interact, create and the grating, beautiful grating pulses. Now, this periodicity can be enhanced over many centimeters of the surfaces also. Okay, so and the grating spacing is much smaller than the wavelength of light. Okay, that I will you can achieve as much even much smaller than the lambda. Okay, but apart from that one, whereas whatever is concerned here, we tried to look at for how we wanted to see the structure. We created, the structure and try to put a low molecule, and we could create, like even metal also. We can create on silicon, we can create on the polymer, we can create on metals, copper, silver, aluminum, anything. Okay, this is what actually we have tried to see how the enhancement is was very, very simple substrate, because our idea was to see we don't want to have an expensive system, but use a different system, smaller system. Okay, so this is what actually. So now we went, like we thought, okay, yes, we will arrange a
No,
1D
Professor,
photo.
sorry to interrupt you. You have
Yeah.
5 more minutes.
Only 5 minutes more.
Yes, Professor.
Okay, yeah. Okay, so we have got these photon band gap systems. Okay, so this is where like we created, and then the 1D photonic crystal structure. Okay, this is actually we created defect layer, and then we could see the structure one cavity mode. Okay, this is one like a metallic dielectric structure. Where we have created, like the polystyrene beads. Actually, now I have to thank, like one of the students who is also a faculty member here in SRM, Dr. Ali, who has been working, who worked on develop, either photonic crystal with a polystyrene, and then we created an inverse silica opal where we could remove the polystyrene beads and create a silica structure. Okay, and then we use that one. This is actually a gold incorporated into the inverse silica opal structure. Okay, where and then we tried to look at the Raman. We took an example of benzene thiol, and we could create a beautiful the Raman signal. Okay, that's I will tell you the history. Like I mean, because we found 632 nanometer. Normally, for a metal gold, you see as the wavelength is increases, you should valence decreases, you should see increase in the signal. But here in the photonic crystal decreases, the change you show a different change, mainly because whether the light is confined on the which edge, whether it is a air band gap or dielectric band gap. So where the field confinement, according to the confinement, you see a change in the one. Okay, this is what the simulations, and you see a beautiful changes into the simulations. Okay, that's what actually we have been. Okay, so this way we do the same thing experiment with a silica. Okay, silicon. So silicon wafer, we created a photonic crystal through etching process. Okay, so you can create the same beautiful the refractive index variations. Okay, by proper etching, so that you can create a high density, low density. Okay, so that is where actually this is and you can incorporate with the gold whatever particle that you want. You can actually attach your metal nanoparticles into the structure and then use it for your Raman signal. Okay, right. So this is where actually we have seen, like in terms of the Raman signal that we have seen. Okay, and then I will show you one crystal. This is the what we now we thought, like we'll create a I'll complete in just 2 minutes. Okay, this is a RS sputtering system. So we created a beautiful photonic crystal structure. This is where actually it has given a very good results to us. Okay, where we have seen just this is we said I told you where we can show the nonlinear absorption studies. We have taken a test molecule as a zinc oxide. Okay, and we tried to see same thickness and same material we have put on a surface of a glass plate, and then inside the photonic crystal, the kind of a nonlinear absorption that you see, orders of magnitude that we see an enhancement into the order. So that means the field inside for the same intensity, same thing, that you see a huge enhancement into the nonlinear absorption. Okay, so we continued with we demonstrate that it's a beautiful optical limiter. Okay, compared to what instead of using like a regular on a film, then you can use it like a one. So we have now achieved lots of this is a barium titanate, another material that we have taken. We have seen a beautiful switching also. So that means switching you can have, depending on the photonic crystal angle, you can have either saturation of absorption or reverse saturation of absorption. Okay, that is a beautiful like a switching. So now once we have got this is another system. Okay, but it is the same thing which I don't want to go through. Okay, this is our the mode calculations. How our field is confined in the symmetric cavity and how beautifully we can confine in the unsymmetric cavity, so that we can field confined within the cavity. So and then reach. This is what you can try to see the lasing action within the cavity. Actually, in this year also, somebody came out with a beautiful micro cavity lasing action in Nature Communication. They have published in Nature Communication. They have shown a micro cavity lasing. So it's almost, the concept is almost like we were working with a not such a good phosphorus one, but you can see that the line narrowing, which is indicating that a multiple pass inside the medium. Okay. Yeah, this is of course this is another beautiful result which we got very recently, a diode action. Okay, that means like we can put a crystal like nicely, it's like a satchel absorption medium one side and reverse satchel absorption medium on the other side. So light passing in one direction experiences in two different ways. Okay, that's what actually you can see. One side it allows and the other side it doesn't allow. Okay, but this is only for the high intensity beam. But provided if we have a good media which can work at a very low intensities, probably this would work like a nice dielectric medium. Okay, this is what actually I wanted to say. Okay, and ultimately I like to thank, these are all beautiful results that you can have photonic crystals. Okay, and then in LED efficiencies, people can use it very beautifully. We have been working on this is what I was telling you, the Nature Communication paper very recently, where they demonstrated emission of light in the one at different wavelength. Okay, beautiful one. Now I like to thank you people have been listening very patiently, and if you have any questions, I will try to answer that one. Okay, thank you very much.
Thank you very much. Thank you very much, Professor Rao, for this very interesting and exhaustive presentation. And now we have time for some question. There is a question in the chat.
Yeah.
And the question is about is asking, what is the role of size homogeneity in the determination of photonic band gap?
Normally it depends on the kind of wavelength that you are choosing. Suppose if you are choosing around 500 nanometers, you want to have, the light should experience the wavelength of whatever is the light, and the media, the dielectric sphere should be much smaller than that one. Suppose like a few 50 nanometers, 100 nanometers would be very good for your 500 nanometer. Suppose if you can go to the longer wavelength, 2 microns, 3 microns, my sphere size could be as large as a few hundred nanometers, 500, even 600 nanometers. So it depends on the wavelength of choice.
Great, thanks again. Thanks for answering, and thanks again for your very interesting and inspiring talk. Thank you very much. And I think everybody join me to thank you for this very interaction. Very let's say interesting talk.
Thank you. Thank you again.
Thank you.
Thanks. Thanks.
Thank you.
So it is now time to introduce the next speaker. Is Professor Bhavtosh Bansal. Is here?
Professor,
Hello, yeah. Can you see me and can you hear me?
Yes, we can see you. Good morning. Good afternoon. Okay, so Professor Bhavtosh Bansal is from the Indian Institute of Science, Education and Research in Kolkata, India. And I guess he's going to talk about photoluminescence spectroscopy in pulsed high magnetic fields.
Yeah, shall I start?
Yes, sir. The floor is yours.
Thank you so much. I hope everybody can see my screen.
Yes, we see your PowerPoint presentation
okay, right?
utility, not the main screen.
Oh, you don't see my main screen? I'm so sorry. Yeah.
Yes, it's better if you can switch to the presentation screen.
Check that. I'm so sorry. Yeah. Let me just try this again. I'm so sorry. I guess I do the whole thing, maybe, no? Sorry. Let me just try this again. So what do? I just maybe I. Yeah. Okay. So I just I guess share. That's
okay. Go ahead in this way.
Yeah,
no problem.
I'll just go ahead.
Yes, yes.
Okay. I'm so sorry. Yeah. So yeah, I'm Bhavtosh. I work at ICONN Kolkata, and it's a real pleasure to be talking to you. And I'm been very, very impressed with the kind of work which has been coming out of the SRM University also. In particular, I've been familiar with some of the work on semiconductor physics. And I'll take this opportunity to just talk about something which is perhaps a little unusual, but I thought it may be of interest to some of the people. And this is regarding doing photoluminescence measurements on semiconductors in high magnetic fields. So I'll try to sort of motivate why one should do that and what kind of information one can get. And part of the talk, say maybe a few minutes, I'll also spend on describing such a setup which we have made in our laboratory with the aim of encouraging others also to perhaps make something, replicate it or make something better on their own. Because yeah, so that's pretty much the plan, as I said. And I'll not be giving a very broad overview, but we're talking about somewhat specifics. And so essentially, as I said, I'll talk a little bit about photoluminescence spectroscopy, pulse magnets, and why one should sort of, what's the point of using photoluminescence in high fields. And then we'll talk about a couple of recent examples which we've been working in our lab. One's got to do with the luminescence in halide perovskite, hybrid halide perovskite semiconductors. Another one is looking at FRET, Foster resonance energy transfer mechanism, and how that gets affected in high fields, and what one can say about studying such things. So this works, of course, done by students, and mostly it's the PhD work of Kingshuk Mukherjee, who's in the group at IISc Bangalore, and my colleague, Professor Malingam, here at ICONN. All right. So just to get started, I should emphasize, so yeah, luminescence is, of course, a very common and popular technique. And luminescence is essentially any non-equilibrium emission of light. So of course, any solid body or any body would emit black body radiation. But it's called luminescence. This emitted radiation is called luminescence if it's non-equilibrium. You have to sort of affect it either through carrier injection or certain non-equilibrium chemicals to drive the system into a non-equilibrium state, and as it relaxes through the process of spontaneous emission, you get luminescence. And when sort of this drive happens by optical excitation, then it's called photoluminescence. And so it's something which I think most in the audience would know, but nevertheless, for the students, so photoluminescence, you can think of an idealized semiconductor as a valence and a conduction band, and with a certain energy gap, E subscript G. And then typically you excite this material with a wave light whose energy is larger than the gap. And then very quickly, so you generate electron and hole pairs, which very quickly relax onto the bottom of the conduction band and the top of the valence band, after which, after some time, so this happens pretty quickly on a time scale of a few picoseconds, after which they recombine to give out light, typically of energy, which is of a larger wavelength or smaller energy than the incident light. So this process happens by spontaneous emission. That's what's called photoluminescence. And it's important for a variety of reasons, because one of the fundamental characterization tools for a long time for semiconductors, because it tells you about defect states and whatever states which can radiatively, in this context, of course, I showed the actual band gap states. So whatever radiatively recombining states which are there are easily captured by the recombination spectrum, which can be measured. And under special circumstances, when the material is clean, so you have these electrons and holes which are opposite, which carry opposite charges, and on account of their carrying opposite charges, they can form bound states for a reasonable amount of time, say of the order of a few nanoseconds in the context of a direct gap semiconductor. And so these bound states, because you have are hydrogenic, because in the first approximation, because you have a positively charged hole and a negatively charged electron. And so these are hydrogenic, so you can think of these excitons as hydrogen atoms or positrons, because they also ultimately annihilate to give out light. So of course, yeah, and in this case, one of the main differences between an exciton and a hydrogen atom is that the binding energy of the exciton is typically 1,000 times, order 1,000 10 to the power 3 times smaller than the hydrogen atom. And that's because if you look at the binding energy formula, assuming a hydrogenic bound state, so there is a term for the mass. So the mass mu, it's written as mu here, becomes the effective mass, which is of the order of, say, a factor of 10 smaller in a semiconductor, plus the electron or the hole actually move in a dielectric environment instead of vacuum, and that adds another factor of 10 or so. And since it comes as the dielectric constant squared, so you get a factor of 100 there. So on these accounts, the binding energy of excitons is a factor of 3 larger, and similarly, the Bohr radius is the binding energy is much smaller, factor of 3 smaller, and Bohr radius is larger. So just as you would expect for hydrogen atoms, of course, they have a bound state structure, and you can think of center of mass, and then you'll have these bound state levels n equal to 1, 2, 3, and so on. And so this is, of course, this is some very old, well-known result. For instance, for gallium arsenide, you can see so before, so and the exciton, because on account of the binding energy, the emission is actually at an energy which is smaller than the gap. So you have the band edge here, and before that band edge peaks, you get various sharp lines, and these lines correspond to the excitonic peaks. And this is what I said, that the exciton is much larger. The Bohr radius for a hydrogen atom was just around 0.5 angstrom, which becomes 5 nanometers on account of this small effective mass and the large dielectric constant. So the point is that these binding energies being so small lead to 2 consequences. So firstly, the binding energy is typically much smaller than the thermal energy, which say at room temperature, which is say of the order of 25 electron volts. So at room temperature, most of the excitons in materials like gallium arsenide would be all ionized. And secondly, because these can act as actually model systems which exhibit hydrogen-like properties, Whereas the energies for hydrogen atoms are very, very large compared to some other laboratory scales. For instance, 13 electron volts, as I'll show, is a large energy. Whereas when you get to many electron volt energies, you can actually apply large magnetic fields and electric fields to perturb these. So this actually has interesting consequences. So as I said, so you have this bound state spectrum, and if you have a very clean system, then you typically see many such bound states. And one extreme example is cuprous oxide, where you can see levels even up to n equal to 25 or so. This has a somewhat larger excitonic binding energy. And typically, the binding energy is a function of the gap. And so this is again a very old classic plot, which shows that so it can go up from something like 1 milli-electron volt to hundreds of milli-electron volts for things like copper chloride and things. But typically for most semiconductors, it's within the range of 10 to 100 milli-electron volts. So the questions which one would like to answer are that, so if you look at emission, and emission, of course, is very, very important for various reasons to study. So one would like to sort of understand if the emission in the material is excitatory, because of course there's another channel, you just simply have electron and holes recombined. So one would like to know whether the material actually has excitonic emission. Then what are the properties of these excitons? For instance, what are the binding energies? What are the radii? Then one would like to know whether things like quantum confinement affects how those affect the excitonic properties, whether alloying affects these properties. Then the excitons can form bound states, so they can be free. So all these questions are of interest both from the point of view of fundamental physics, because you can try to understand the electronic states within the material, as well as from applications point of view. And what I'll try to argue is that high magnetic fields help answer many of these questions, in fact, all of them to some degree, and many more. And so that's what I just try to argue now. So yeah. So the main idea is that even if you think of just a simple bound state, the ground state of a hydrogen atom, which is just a s orbital, the 1s state, and similarly for an exciton also will have such a 1s state. And so even if there's no sort of magnetic moment associated with such state, so those are the states we'll be talking about in this talk. So, but before that, so if you just think of a free electron in a magnetic field, then as we all know, that as soon as you apply a magnetic field, the electron is constrained to go in cyclotron orbits. And so this is of course a classical picture, but this picture also goes through quantum mechanically as long as the field is large enough so that the electron can complete a few cyclotron orbits before it scatters, which is to say and so that requires a certain somewhat large strength of the field. And but once you have that condition satisfied, then you can define a length scale, which is called the magnetic length, which is just a function of fundamental constants. And so basically, what this means is that magnetic field is confining the electrons to go in circular some kind of cyclotron orbits, and these cyclotron orbits come with a characteristic length scale, which can be tuned by applying a magnetic field. So magnetic field actually acts like a ruler, because it's as soon as you apply a field, the larger the field, the smaller the cyclotron radius. So what the main idea about using magnetic fields is that you can apply the field, and that confines the motion to a cyclotron orbit, and you can compare this confinement with a certain other confinement which may already be there, either which is imposed materially by the boundary conditions, as in the case of quantum dots or nanoparticles, or just the simple hydrogenic bound state, which again has a characteristic length scale, which is a Bohr radius. So that's basically the idea. And so when we sort of talk about large magnetic fields, or for the magnetic fields to have a substantial perturbation on the ground state or the state of the electrons, then of course you would expect this to happen only if the cyclotron radius is much larger, or sorry, it's much smaller than or is at least comparable to the other characteristic length scale in the problem, which in this context would be the Bohr radius, as I discussed. And so it turns out that for a free hydrogen atom, this turns out to be a very, very large number, which is something like 240,000 Tesla. But on account of the reduced binding energy and the larger Bohr radius for the exciton, which is this becomes a factor of much, much smaller, and something like even 10 Tesla turns out to be good enough field. So this is what, again, I just sort of tried to explain, that we had this hydrogenic, so the hydrogen atom has a certain length scale, which is the Bohr radius, and there's another length scale which is automatically imposed with the magnetic field, which is the cyclotron orbit radius. And basically, the cyclotron orbit radius scales as under root of the magnetic field, 1 by under root of the magnetic field. So the point is that you can change the cyclotron radius continuously by increasing the magnetic field. And when the cyclotron radius becomes comparable to the Bohr radius, then the magnetic field becomes a strong perturbation on the orbit. And by seeing how the energy levels shift as you apply this large magnetic field, you can sort of figure out what the Bohr radius and the binding energy of the basic system which you were studying was. So that is basically the idea. Yeah, that's again exactly what I said. So please stop me if there are any questions, and the chairperson may please, remind me of when I have like 5 minutes left or so. So yeah. So this is yes, this is again something which I had already said. So yeah, so the fact that in semiconductors, on account of larger dielectric constant, smaller mass, so this 3.5 Tesla, for instance, in a classic semiconductor like gallium arsenide. So we saw that the Bohr radius is equal to the cyclotron radius for 240,000 Tesla for a hydrogen atom, and this 240 Tesla becomes something like 3.5 Tesla for gallium arsenide. So already at 3.5 Tesla or so, you start to see strong field effects, and so that's why laboratory scale magnetic fields of this order can be useful. So the point is that you can use superconducting magnets to perturb the system which have smaller binding energies, but as you get to systems which have binding energies of the order of 10 to 30, 40, 50 milli-electron volts, then you need fields which are much larger, and that's what I'm discussing. Okay. So the question is, how exactly does the energy level, how exactly do the energy levels get perturbed? And one can so this is an equation taken from Ashcroft and Mermin on the chapter on magnetic properties of materials. And so basically, so there are basically two kinds of effects which happen when you apply a magnetic field onto bound states of electrons. So the first effect is this paramagnetism, which comes for states with non-zero angular momentum. So and so there are two terms for that. But when you're looking at the ground states, then the angular momentum is zero, because you're looking at S equal to usually the S state, S levels. So in that case, only this diamagnetism term survives. And in the weak field limit, the prediction is that the shift of the energy level with magnetic field goes as B squared. And the coefficient of this B squared term actually contains two terms, apart from this fundamental constant, the electronic charge. And the two terms are the effective mass of the bound state, which is the effective mass of the exciton, and the effective radius squared. So basically, that's basically the idea, that quantitatively one looks at the shift of the ground state energy levels of confined systems in magnetic field and see how they shift. And from the coefficient of the B squared terms, one can simply, so yes, this is the simplest thing which one can do when one is studying systems in high magnetic field. One can get the value of, if one of the two is known, then you can get the other. So yeah, so that's basically the idea. And this is, for instance, an example of a measurement done with a superconducting magnet, and again on old-fashioned gallium arsenide quantum wells, where you can actually see. So there's a shift in the, so this is the photoluminescence emission spectrum plotted as a function of magnetic field. You can see it shifts, and it shifts to lower wavelengths, which means high energy, which is seen here. And so the shift actually is quadratic, and then you can get various parameters. So basically, this is yeah, what one would expect. And so the argument which I had given was only for weak fields. And when you get to very, very strong fields, then basically the effect of Coulomb confinement is negligible. And well, I should not say it's negligible, but then essentially the Landau level effects become stronger, and that's why you get linear independence. So basically, if you look at the field dependence in general, it would go as quadratic. So this is on a log-log scale, so there are two slopes. So it starts as quadratic, and at very large fields, it tends to linear. All right, so this is what I said. So in the low field, you would expect the shift to be like V squared. And this is another spectrum taken from hybrid halide perovskite sample, which has, so this is one of the materials which I just been describing, whose parameters, for instance, whose Bohr radius you would like to determine. And here, so this is a spectrum which is measured at 0 temperatures. There are 2 peaks, and we see that each of these 2 peaks shift a little bit. It's this red curve is the spectrum measured at 35 Tesla, and you see that there's a slight shift in the peak. And for using these kind of shifts, we will try to determine the Bohr radii and the binding energy and the effective mass. So it should be actually a squared. Okay. So with this, I think I would take this opportunity to spend some time in describing how, so because say for instance, this is a spectrum which is measured in our lab at different fields. And so I would like to describe, because I think it's kind of interesting on its own, and it's something which I think many more people can actually develop. It's a powerful technique on their own. So I'll just describe what is the idea of generating such large fields. And so one thing which one should sort of note is that when we're talking about magnetic fields, 1 Tesla itself is a very large number because the value of the mu naught, the fundamental constant, which is the permeability of vacuum itself, is so small, so that if I were to just make an iron solenoid or just copper solenoid and drive some current through it, then I would say if I just use this formula, B is equal to mu naught Ni, and is the number of turns per unit length, then because mu naught is so small, I would need something like 1000 amps to generate 1 Tesla, roughly speaking. And so if I put in some value for the resistance, you can see that I'll need something like 100 kilowatts to a megawatt of power to generate 1 Tesla. Of course, the way it works in the lab is that you put in some iron core or some soft ferromagnet core, which has a large permeability, and that sort of pushes up the field. But the problem is that these saturate beyond 1 to few Teslas, and then you have to go back to normal solenoids. And then what one does is, for instance, one of the, of course, popular ways to make a superconducting magnet, but these, of course, also saturate because of various constraints. So the normal superconductors, which use liquid helium, can go maximum to something like 18 to 20 Tesla. And nowadays, there are like prohibitively expensive systems around like even 30-35 Tesla magnets with high TC, which are being tried and which are being made actually. These are again very, very expensive and still under development. So then basically what one does is to go back to DC fields, and what you do is to there's no option but to pump in a lot of current through these copper coils, and then the maximum field which one can get is something like 45 Tesla. Many places in the world, including China, now have fields which are the order of 45 Tesla or so in these magnets. Yeah, so let me just skip this. So this is what one can conventionally do, but another sort of a nice idea, in my opinion, is to just minimize the time, because the field of course, is proportional to the current, and heating is proportional to current squared times resistance times time. So if you can minimize the time and just have the field on at the transient, which lasts only a few milliseconds, and these milliseconds also, of course, is a very long time, because the radiative lifetimes are, say, the order of nanoseconds. So it's still, million times a radiative lifetime, typical radiative lifetime. So if you can just finish the experiment before the coil gets too hot or too much power is dissipated, then you can basically make a small high field system, and that's what the idea of a pulse magnet is. So in a pulse magnet, what you have is basically a bank of capacitors, a power supply, and a coil. And what you do, so it's basically just an LCR circuit. And what you do is you just charge up the power supply, charge up the bank of capacitors with the power supply, and close the switch. And as the switch closes, you have generate a large transient, and which can last up to a few milliseconds. And during this few milliseconds time, you finish off the experiment. So yeah, and yeah, so it's just basically you have half CV squared energy, which gets dumped into inductive or magnetic energy, and yeah, and that's what generates a large transient field, and during this time you do the measurement. And so this is the kind of facility which we have sort of built at ICER. The students, mostly undergraduates and some PhD students later on, have sort of developed. So you have a generator circuit, which I just described, and I'll be just describing optical spectroscopy measurements here. So generator circuit, the generator circuit actually has a bank of capacitors, and these capacitors are actually all locally procured. They're just these electromagnetic capacitors. And what you just do is, so this is the high current circuit. So you have this charging unit, which just charges this bank of capacitors to around 500 volts. It can go up to 500 volts. And once you charge these up, so this is what the bank of capacitors looks like. So it's all sort of made at home. And I'm sorry, I'm just showing this mostly because if anybody is interested, I would be very, you're most welcome to visit. And yeah, we can of course do measurements together, but also if anybody would like to replicate a smaller or a larger system, then I would be most delighted to help and assist. Yeah. So once you have this bank of capacitors, the second thing is the magnet coil. And here again, it's interesting because one of the problems is that beyond 20 Tesla, the stress in the material is so large that most of the materials would actually explode because of the Lorentz forces which they experience. So it's basically the coil is like a pressurized coil in a magnetic field, or coil generating magnetic field is like a pressurized vessel. So the only way to make a coil is actually to reinforce the material by some high strength fiber. For instance, if you just choose soft copper to wind the coil, then beyond around 22 Tesla, the pressure would be so large that the coil would explode, and so on. So what one does is that you make a layer of copper, but then they reinforce it with a high strength fiber, and so one calculates the stress in each layers, and ultimately one sort of designs a coil which just simply looks like this, where you have this copper layer which are reinforced, and with such a coil one can sort of get a field like this. This is a field in our lab for which sort of rises in around 10 milliseconds, and then it sort of goes on to another 20 milliseconds. And you can sort of, by charging, by controlling the amount of energy which you put into the bank, you can change the field. So yeah, so that's basically, as I said, the setup. So you have the bank of capacitors and some switches which you can just close and dump this energy into the bank, into the coil. Yeah. So yeah, okay. And so when we're doing photoluminescence measurements, then what one needs to do is to synchronize this field with the detectors or the spectrographs which one is using. So for these measurements in the visible, we use electron multiplying CCD detectors, which are pretty sensitive. And so with the exposure times of say 1 millisecond or less, one can actually generate enough light to measure the photoluminescence spectrum. And so what you have to do is to sort of make sure that you open the shutter only for a small amount of time around the place where the field is more or less constant, and you do this measurement. And, or you could also, say if the shutters at times are shorter, then you can open them at other places also, and you can measure many spectra during the field. So each one of these spikes here are basically showing that where the shutters may have been opened. Okay, so you can do that, and you can sort of do this multiple times, and very quickly you can measure the field dependence of the field dependence of the PL spectrum. So that was one part, and then what you do is then of course you have to make a cryostat. So we have two cryostats, one which is closed cycle based cryostat, so homemade, which can go up to around 10 Kelvin, 9 or 10 Kelvin base temperature. The other is just a simple liquid nitrogen cryostat. So here what you do is that you have a laser which excites the sample. So you through a fiber optic cable, and then you collect the luminescence through another fiber which goes to the spectrograph. The spectrograph is sort of synchronized with the field pulse, so that you can do synchronous measurements as in when you want to sort of open the shutter, during which time. And inside, of course, you have the sample insert where you can control the temperature, etc. So this is this is what it looks like. So this is what the setup is. So this is it looks a little complicated. Basically the same thing. So partly it shows the high current. This is the high current part, which is the coil. This is the capacitor bank. This is the charging unit, and so this is one part. Then the second part is the actual. This is the spectrograph part, where you can actually do the measurement by the fibers coming in and out of the cryostat here. Yeah. So what this is all, what I want to emphasize is that this is actually all rather straightforward to actually make yourself, if you sort of do that. And this is some pictures of this. Yeah. So this is I said that. So we'll try to just open the shutter during a short enough time, such that of course the field is changing always. So you have to make sure that delta B by B, the rate of change of field, the fractional change of field, is within a certain acceptable value. Okay, so let's come back to the measurements of halide perovskites. So as many of you know, these are extremely important and interesting materials, and in the context of groups which are working on low budget, they've been very attractive also because these are rather easy to grow through the solution route, and they have extremely interesting properties. And so there's a whole class of materials, different kinds of materials, and a lot of them behave more or less like semiconductor physics, conventional semiconductors, except that they're just far more defect tolerant. But otherwise, a lot of these aspects, so it's actually still not completely understood as to what aspects are really like basic semiconductors and what aspects are somewhat different. And one of the things which one would like to know and do is to really characterize their fundamental properties. And so in this context, so we sort of focus to this here. I'll just show some results on this hybrid material, which is so there's a common popular hybrid perovskite called MAPBI3, and so we've studied this material. So what I'll show is some results on this, and in particular, you can, so it has certain certain disadvantages in terms of stability, and so what people have also been trying to do is to look at an alloy where you have two metal organic ligands, Fa and Ma, and so these are alloyed together, and you have Fa PBI3 and Na PBI3 in certain fractions. And what one would like to do is, and so if you just mix them, actually, it's you get a pretty complicated phase diagram. So here, the phase diagram. So this work is done with in collaboration with Professor D.D. Sharma's group at IC Bangalore, and so here, when you sort of mix them, so this is just the phase diagram which they discovered some time ago, and others had also found this. So you should change the Fa content in MAPBI3 from 0 to 1. And as a function of temperature, you get various phases. And what one would like to do is to look at the exciton behavior in these phases. And this is what I just described. And the binding energy is known to be rather large, so you need large fields for this. So that's what we'll try to do. So yeah, so this is what I showed you. So if I just look at this phase diagram, so I'll just maybe just describe. So this is, say, for instance, one concentration, Fa of 0.4, and you just do the measurement. And so you have these two peaks. So these two peaks actually, so as you can see, this peak, if you just look at it a little carefully, then this peak you can see shifts a little more with magnetic field than this peak. And since the shift itself is proportional to the radius, so this means that this peak corresponds to states which have a larger radius than this state, these peaks. And this is something which is quite characteristic of most semiconductors, that the excitons also form shallow bound states. So this is most likely a free excitonic state, and this is most likely a shallow bound state. And so these two radii also turn out to be slightly different. And so both of them seem to have this B-square dependence, as one would expect from perturbation theory. So what we have done is that you can just keep doing these measurements at different temperatures, and then you can, so this is some other fraction, and you can do that, and you can just keep filling this whole phase diagram. So these values are the values of the inferred values of the Bohr radius. So you can get the whole Bohr radius, so you can get the values of the Bohr radius across the plane pretty much. So actually we've also measured one. So yeah, so you can get the Bohr radius values. So this is, yeah, and here you can see, so the Bohr radius seem to be increasing with increasing temperature, and also they seem to increase as you go, as you increase the mole fraction of Fa up to around 0.4, after which they seem to be stabilized. So yeah, so this is kind of a work which you can do, and for many different materials one can do that. Yeah, so that's how much time do you have?
Sir, 5-4 minutes.
Okay, so okay, including questions, or maybe okay, I can take another 2-3 minutes. Okay, let me just take another 2-3 minutes.
Yes, sir, you can present for 5-4 minutes.
Okay, fine. So yeah, so the last thing, okay, so this maybe I can just leave this bit out. And so last thing, again, another example which we've been, again, this is also unpublished work. So this is some study of field-induced suppression of resonance energy transfer. So as we know, so this is actually again, so okay, so I'm shifting gears a bit now. So this is, so there are a lot of molecules in various contexts actually. What can happen is that you have two species, and you have, for instance, a donor species and an acceptor species within the same system. And what can happen is that you excite the donor species. It is some molecule which you excite, or some atom which you excite, and then there is a non-radiative transfer of energy from the donor species onto the acceptor species. And one classic example of this is what is called Foster resonance energy transfer. So the Foster process is, so there are two processes. One is this Dexter process and Foster process. But so this Foster process is this radiationless process where essentially it's like these donor and acceptor species act like antennas, and there's this transfer of energy from the donor species to the acceptor species. And this is kind of, it works if the distance between these two is of the order of 10 nanometers or so. And it sort of has a very strong dependence on the distance. It's like R to the power 6 or upon R to the power 6 dependence. So one of the well-known systems, which I think maybe some of the people in the audience may already know quite a bit about, are these lanthanide ions. And for instance, this ytterbium and erbium ions, this is again a very popular combination of lanthanides, where YB actually acts, YB3+ acts like a donor, and erbium acts like an acceptor. And so what you can do is you can excite the ytterbium ions, and actually it turns out that you can, so these actually work also because there are 2 photon excitations. So actually you get enough conversion, but that's not very important for our purpose here. But basically you can excite the erbium ions and then you get emission spectrum, which belongs, so you can excite the ytterbium ions and you get the erbium excitation spectrum. The spectrum which you get is the emission from the erbium. So yes, this is what the process is. So basically you have a donor and acceptor atom, and so you first excite the donor atom, and then there is a transfer of energy, radiation, and it's a resonant transfer. The energy gets transferred from donor to acceptor, and then the acceptor finally has the energy which was earlier the donor, and then acceptor radiatively recombines, and you get the fluorescence out. So one of the probes for this could be, so of course this is very, very well studied by biologists, especially biologists and chemists. So one of the things which one could sort of ask is, how does this get affected when you apply a magnetic field? And you typically need a pretty large field to affect this. And so this is some measurements which we have done. So these are done with my colleague in the chemistry department, Professor Venkatramanan Malingam. And so you see, so as a function of, so these are pretty complicated spectrum, which I just mentioned briefly. But basically you have 2 bands or 3 bands, and each one of these bands actually gets suppressed when you have a magnetic field. The actual spectra is very, very complicated because these are these F electron levels, which are actually all mixed up because of because there are these crystal electric fields which cause this Stark shift, and all the selection rules and the degeneracies get lifted, and you get a whole zoo of levels. Actually, you get a very, very complex structure. So this is just to show that the actual structure can be very, very complex. And when you look at the energy levels, so some other work which we had done where you can identify so many different transitions. So it's actually a complete mess. But if one were to just look at the overall intensities and just think of these as, so of course, so what I'm saying is that this actual structure, of course, comes from the energy level structure of the erbium atoms, or the erbium ions, erbium 3+ ions. But the intensity, the bottleneck for the intensity is this FRET process, which sort of told us as to how efficient this transfer was, right? So as far as the FRET process is concerned, one would say one could perhaps just look at how the intensity itself is changing with magnetic field. And when you do that, then you observe 2 things. The first thing which you observe is that the field, the intensity systematically decreases. These are 3 different samples which are basically grown in a similar way, but they are still, they are quantitatively similar, but in actual terms, in actual quantitative terms, the results are a little different. And we can discuss that if you have a question. But basically because it will be very sensitive to the local environment, because the kind of electric field perturbations which you generate will actually affect the response very strongly, I would imagine. But nevertheless, so you see that there's a decrease in the intensity, and there's roughly a B² dependence, because I've plotted this as B² versus the change in the intensity. And so then one can actually do a simple calculation where you can think of FRET is basically some kind of a photon exchange between the donor and the atom, the acceptor atoms or the ions. And if you just think of a very simple process where there's a dipole interaction, then one can actually show that indeed it would be 1 upon r to the power 6 dependence in the leading order, and also that you will have a B² dependence and a F dependence. So basically both the efficiency of this FRET process would depend on both the dipole moments of the donor atom and the acceptor atoms, and those dipole moments themselves get affected as b squared of the applied fields. So overall, you expect indeed that you should get a b squared dependence, and so that's what one has observed. This is again some other published result where people have done measurements to much larger fields, and this also one finds that you actually do see a b squared dependence. So this is again another application where you can see that systematically the luminescence is changing with magnetic field, and we can sort of try to understand the underlying physical process by looking at the change in luminescence. All right, so I'll stop here. So the summary is just that, yeah, you can, it yields, I've given you a couple of examples of how luminescence and high fields can yield interesting information about the materials, the exciton structure, for instance, things like the Bohr radius or the binding energy, which is not very easily accessible through other experiments. And secondly, you are welcome and invited to also try to set up such a system in your laboratory. And I welcome collaborations also in terms of anybody's interested in doing such measurements on their samples in our lab. All right, thank you so much. I'll stop now.
Thank you very much for your very interesting and very interesting talk in this subject, which is not very well known. I think it's something quite new. It's very interesting. Even your experimental setup is very interesting and inspiring also. So the paper is open for discussion. I do not see any question in the Q&A window.
Yeah, Professor, I have a question.
Yes, please.
So with the application of magnetic field, you see the suppression of an intensity. So in addition to that, do you see any additional peaks due to the lifting of degeneracy?
So that is actually very, very hard. So that's a very good question, but that's very, very hard because the spectrum is so messy that yes, things do change, and one can quantify this change also. But it's actually a very messy issue.
Oh.
So yes, so definitely the spectrum itself changes, and it is possible that actual physics of the Zeeman physics actually could be an important contributing factor here. Yes, so that's really important, and which is something which I've ignored here. Yes.
Oh, thank you.
Okay, thanks. More questions? No, I don't see. So I think we can thanks again our speaker, our speakers. Actually, we had a very interesting session, and thanks to both of you. Thank you very much.
Yeah, thank you, Professor Parada, for chairing this session. Yeah, thank you. Participants, we have several parallel sessions going on, so please do join various parallel sessions according to your interest. With this, we thank the speaker and the chairperson. Thank you.
Thank you.
Thank you.